models and analysis. So please, Laura, the floor is yours.
Hi, thanks Daniele and Catalina. So I try to share my screen. So let me know if you can see my slides.
Yes.
Okay, perfect. So thanks a lot for inviting me and for the introduction. I would like to take this opportunity to present research topics on which we have been working in the last 10, 15 years. And so what I'm going to present is the result of joint work with many people, in particular with Professor Enrico Vicario from the University of Florence, with Marco Paulieri from the University of Southern California, and with many other PhD students and postdoc research associates at our lab in Florence. So actually, we have been working on quantitative evaluation methods for non-Markovian systems. So the first question that arises is why using non-Markovian models, given that there is a very vast literature that has addressed modeling and analysis of Markovian systems, and these solution techniques are implemented in very consolidated tools. So first point is that several systems in various application domains exhibit non-Markovian temporal parameters. So temporal parameters that are associated with a non-exponential distribution. And sometimes these parameters are the result of design choices, and typically in this case, they are deterministic temporal parameters. So for instance, this is the case that we have when we implement periodic tasks in real-time systems. And so in this case, we have deterministic inter-release times, deterministic offsets, and typically we also prescribe deterministic deadlines for these tasks, or timeouts and watchdogs. As an example, also waiting times in communication protocols are typically deterministic values. And then there are also many application contexts where the system inherently exhibits generally distributed timers. So timers that are associated with a non-exponential distribution, possibly with bounded support. So for instance, this is the case of durations in aging processes, which of course cannot be accurately represented using memory-less non-exponential distributions. But there are many other examples in various other contexts of embedded and cyber-physical systems. So for instance, inter-arrival times and delays in transportation systems typically do not follow an exponential memory-less distribution, and typically they have a bounded support. Another point in favor of using non-Markovian temporal parameters and non-Markovian distribution is that they facilitate fitting of distributions from observed data, from observed durations. So roughly speaking, if you have an exponential distribution, then you have one free parameter, which you can use to fit the mean value. Conversely, if you use non-exponential distributions, then you can have more free parameters, and so you can fit higher order moments and possibly also the support of the data that have been observed. So non-Markovian models offer expressivity to model real systems in various application domains, and of course this expressivity comes at a cost. And the cost is the complexity of the analysis of the underlying stochastic process. So I don't want to, of course, get into the details of the theory of stochastic processes, but here I would just like to give an idea of how modeling choices affect the complexity and the size of the underlying stochastic process. So first of all, when we mention the stochastic process underlying a model, typically we refer to the stochastic process that characterizes the evolution of the logical location of the system, so the evolution of the discrete components of the state of a system. And there are different classes of non-Markovian stochastic processes, and these different classes differ in the way the process encounters regeneration points. So a regeneration point is a time instant at which the Markov condition is satisfied. And so the future evolution of the system depends on the past only through the current location, or only through the current discrete logical location. So depending on the occurrence of these regeneration points, we can have different classes of non-Markovian stochastic process. The simplest case is when general timers never persist to each other. So general timers are reset after each event. So this is the case that we have in this top figure here. So here we have a stochastic time Petrinet. Here tokens within circular places represent the logical location of the system, while transitions, which are depicted as bars, represent events of the system. So in this case here, we have that a token in place P0 enables this event T0, which occurs after a time that follows a uniform distribution between 0 and 1. So when this event occurs, then a token is removed from place P0 and a token is added to place P1. And this transition T1 is newly enabled, becomes enabled. And so this event, just like T0, will occur after a time that is uniformly sampled between 0 and 1. So in this case, we have that a regeneration is reached after each event, because after each event, the general timers, the general temporal parameters are reset. And so in this case, the process is termed semi-Markov process. If we compose two of these models in parallel, which is what we do here in the bottom figure, then what happens is that the general timers that we have in this model continuously persist to each other. And so it is never the case that we reach a regeneration point. And so after the initial regeneration, this model does not reach any other regenerations. And when we have this kind of model, the underlying stochastic process is termed generalized semi-Markov process. So this is a process that does not assume anything about the occurrence of regenerations. If this transition here, T3, this general transition, is replaced with an exponential transitions, white bars represent exponential transitions, then regenerations can be encountered also after the initial regeneration. So for instance, in this case, we have that T0 and T2 are initially enabled. After the firing of T2, T3 becomes enabled, but T3 is an exponential memoryless distribution. And so when T0 fires, then a regeneration is encountered, because the other general timer enabled is the one represented by transition T1, and this is newly enabled. So in this case, the underlying stochastic process is termed Markov regenerative process. So these are processes where always with probability 1, a regeneration will be eventually reached. This can occur in an unbounded time or through infinite events, but always with probability 1, a regeneration will be reached. And so as I was saying before, these small examples give an idea of how apparently minor modeling variations, modeling choices affect the class of the underlying stochastic process. So changing a transition from general to exponential and vice versa changes the class of the underlying stochastic process. Along the years, various solution techniques have been developed to solve non-Markovian models, and most of the literature has worked under the enabling restriction. So this is a hypothesis that prescribes that in any state there cannot be multiple concurrent general timers. So in each state there can be at most one general timer enabled. And so various approaches have been developed in this setting. Some of these approaches, in principle, in the theoretical perspective, could be applied also beyond the enabling restriction, but in the practice, they encounter too much complexity to do that. An approach that can always be followed is to approximate the model. So when we have a non-Markovian model, a model with non-Markovian temporal parameters, we can replace the non-Markovian distributions in the model with phase-type distributions. A phase-type distribution is the distribution of the time to absorption in a continuous time Markov chain. And so what happens is that pursuing this approach, we obtain a sort of Markovianization of our initial model. And of course, we have to face a trade-off, to achieve a trade-off between the accuracy of approximation and the complexity of evaluation. And in any case, we approximate general non-Markovian distributions with the distributions that have zero infinity support. And so it is not possible to preserve bounded supports. And then the most recent approach is the method of stochastic state classes, which has been developed in the last 10-15 years by our research group. This approach addresses the analysis of models where multiple concurrent general transitions can be enabled in the same state, and possibly they have bounded support. The main idea behind the approach is to compute the analytical form of the joint distribution of the active timers after any event. And so, of course, also our approach faces different complexities. In particular, the approach suffers when we have a high concurrency degree among general transitions. And the approach is also very sensitive to the number of steps that we may have between subsequent regeneration points. And so it is accurate and I would say exact and also efficient where regenerations occur in a bounded number of events. This approach is implemented in a tool which is termed ORIS, which is a tool that supports specification of models using the formalism of stochastic time Petri nets, which I was mentioning before. The typical workflow of ORIS starts with designing a model using the graphical user interface and validating the model using interactive simulation. And then there are different analysis engines available to analyze the model depending on the class of the underlying stochastic process. But the distinctive feature of ORIS is the implementation of transient and steady state analysis for models that underlie Markov regenerative processes and transient analysis of models that underlie generalized semi-Markov processes. Of course, a graphical user interface is useful in the initial stages of model design, but when you have to perform extensive parametric studies and when you want to analyze multiple variants of your model using multiple values of parameters, then you need to export the model into Java code and write, or into code in general. In the case of ORIS, it is Java code, and implement programs that automate model construction and analysis. And in the case of the ORIS tool, this is supported by the Stereo Java library, which is the underlying Java library of the tool. So this is also, I mean, a well-engineered library, which also facilitates the implementation of new features for the PetriNet models, new modeling formalisms in principle, and also new solution techniques. So of course, tasks that could not be performed using only a graphical user interface, clearly. We have non-Markovian models which provide expressivity to represent a large class of systems. We have solution techniques for their analysis, for their quantitative evaluation. And then we have tools and libraries which enable which permit to carry out extensive parametric studies using this modeling and analysis methods. But still, this is not the end of the story. This is not enough because, as we all know, practical exploitation of this potential, of the potential of stochastic models, and in particular non-Markovian models, faces various challenges, and in particular contrasting needs. So when we have to deploy this modeling and evaluation methods, the activity of model construction must not disrupt the practice of the specific context of use. So typically, we cannot specify models using stochastic time PetriNets, but we need to derive our stochastic models from higher level artifacts, typically artifacts of the unified modeling language. And of course, when a model is when a stochastic model is automatically generated from other artifacts, it is not easy to guarantee that the underlying stochastic process can be efficiently analyzed, because, as we have seen in the examples before, skills are needed to accurately model a non-Markovian system, and even small modeling variations may have a significant impact on the class and the size, and so the analyzability of the model. And so in this case, model-driven engineering becomes relevant and permits to reconcile these contrasting needs. So the ORIS tool supports model-driven engineering methods in a process that goes from domain metamodels and arrives to runtime analysis. So as I was saying before, typically we start design models using the graphical user interface. Then we export the model into Java code, and then the program that we obtain can be easily extended to implement a model builder that visits a domain meta model in the end with the objective of collecting information concerned with the specific instances of the problem of the system of the model that we are considering. And in the end, this supports evaluation of quantitative measures for use cases of high level users, system analysts, and so on. And so along the years, we have applied this kind of approaches to dependability evaluation of various systems. In particular, I would like to mention performability evaluation of railway signaling systems, performability evaluation of repair procedures for gas and water distribution networks, and also activity recognition in ambient assisted living, and input generation for real-time testing, for testing of real-time systems with uncertain behavior. And in this specific case, the approach also included generation of the real-time code, so model-driven development actually, so not only model-to-model transformations, but also model-to-code transformations. And so I would like to take the opportunity of this talk to present a recent work that we have submitted in this context, which we have been working on in this context, which is concerned with performance evaluation of multimodal urban intersection. So we have intersections where we have tram lines, possibly made of multiple tram tracks, which intersect car flows. And tram lines have right-of-way over car flows. So in this example here, we have a bidirectional tram line, so a tram line made of 2 tracks, and a single-lane car flow, but we could have multiple tram tracks and multiple car flows. So in this case here, what we have is that we have a periodic phenomena represented by tram traffic, which affects the process of car arrivals and crossing at the intersection. And so the objective is to evaluate the impact that tram traffic may have on car traffic. And in particular, we would like to evaluate the expected number of QR cars over time. And we would like to perform the evaluation over intervals having arbitrary duration, so that we can use the approach to perform what-if analysis and also select a convenient schedule for car semaphores, but also a convenient offset for different tram tracks. And to do so, we combine transient and steady state analysis, because of course, as we all know, we do not need to have a driving license to understand that the expected number of QR cars over time does not reach a steady state. But we can easily prove that the distribution of the expected number of QR cars actually reaches a steady state at multiples of the system hyperperiod, which is the least common multiple of the periods of car semaphores and the periods of tram track arrivals. And so this is the meta model that we consider. So as I was saying before, we have independent tram lines. Tram lines are made of multiple tram tracks, and tram tracks are characterized by a period, which is the period of tram arrivals, by a phase which can be associated to complete the characterization of the arrival process. And then we may also have a generally distributed delay, because of course, as we all know, trams are not, typically they are not exactly on time. Of course, this is a fact. And we also consider a general distribution for the time needed by trams to cross the intersection. And then on the other side, we have car flows. So car flows are characterized by other parameters, in particular, car flows are associated with a semaphore, and all the semaphores of the car flows have the same period, but they could also have different periods, but we consider the same period just to simplify the presentation. And then we consider for the inter-arrival times and the intersection leaving times, exponential distributions. So this choice subtends the fact that, of course, we cannot have a monolithic non-Markovian model accounting both for tram tracks and for car flows, because we could not afford the complexity that we have when the queue size increases. So the solution technique, the analysis of the model could not scale with the queue size. And so in the end, we resort to a compositional modeling and evaluation approach that combines two different models. So a microscopic model of tram traffic, which is represented in terms of stochastic time Petri nets, and a microscopic model of car traffic, which is represented in terms of finite capacity queues. And so starting from our meta model and from specific intersection parameters, we visit the meta model and we are able to generate these models. So the stochastic time Petri net models of tram tracks and the finite capacity queues modeling the car flows. The models of tram tracks can be analyzed, and they provide the intersection availability. So they provide the probability that the intersection is available for car flows over time. And then we can perform transient analysis of the queue behavior, considering that the intersection is not always available. And then, based on this, as I was saying before, we can also perform steady state analysis of the queue behavior to derive the steady state distribution of the number of queued cars over time. And so this combination of transient and steady state analysis is what enables the evaluation of the expected number of queued cars over time intervals of arbitrary duration, because we can start transient analysis from the steady state distribution that we have reached using the previous parameters of the considered intersection. And so a few details on these two different models. So this is the microscopic model of tram traffic. And so these gray bars represent deterministic transitions, so transitions that are associated with a deterministic value. And so the process of tram arrivals, as I was saying before, is characterized by periodic departures. These periodic departures can also be characterized by a phase, also offset. This is typically termed offset if these were not trams but tasks in a real-time system. And then we have a delay, which in this case has a uniform distribution between 0 and 120 seconds. And this is the delay with which the tram arrives at a wayside system that is positioned near the intersection. When the tram arrives at the wayside system, then the car semaphores are triggered red. And so these 5 seconds that we have here are actually the time advance with which the car semaphores are turned red before the tram crosses the intersection. And then we have a uniform distribution between 6 and 14 seconds, which represents the time needed by a tram to cross the intersection. So I would like to stress the fact that in this specific case, we have fit the available data, which were provided by the company that manages the Florentine tramway. We have fit this data using uniform distributions, but in principle, we could use also other distributions. In particular, the ORIS tool supports the class of X polynomial functions, which are a quite general class of functions, possibly with bounded support, possibly piecewise defined over a specific domain. And so this is the model of a tram track. We can analyze separately the model of each tram track and combine the results. And finally, what we obtain is the transient probability that no tram is occupying the intersection. So, for instance, in this case here, we consider two identical tram tracks, and so the dashed line is the probability that no tram of a single track is occupying the intersection, and the black line is the probability that no tram of any of the two sections is actually occupying the intersection. And so this probability is used to modulate the service rates in the macroscopic model of car traffic. So in particular, we represent car traffic using finite capacity queues. We have experimented with MM1K queues and with MMKK queues. So in the former case, the intersection is considered as the server, and in the case of MMKK queues, it is the street preceding the intersection that is considered as the server. So in this case, the model is characterized by a birth-death process, and we can define ordinary differential equations which characterize the number of queued cars over time. So nothing special in this model. I would just like to underline the fact that the service rate is modulated by the probability that the intersection is available at time t, and the car semaphores also are green at time t. So this is modulated by a quantity that depends on the analysis of a separate non-Markovian models. So we can perform transient analysis and in the end compute the expected number of queued cars over time. And so we obtain, assuming that the queue is empty at initial time, we consider in this case an intersection with a car flow and a tram line made of two tracks. And we obtain this pattern here, where, of course, peaks correspond to the time instance during which the probability that the intersection is available is larger, while troughs correspond to the cases where the probability that intersection is available is lower. In particular, we can see that the MMKK model achieves slightly lower peaks and higher troughs. And this is mainly due to the fact that the multiple server semantics makes the queue fill and empty earlier, and so in the end the peak to trough amplitude is lower than in the case of the K1 model. Then we can perform the steady state evaluation and compute the steady state distribution of the number of queued cars over time. So this can be proved. I don't want to get into the details of this. But as I was saying before, this enables the evaluation of the expected number of queued cars over time for time intervals that have arbitrary duration. So in this case here, we have the same curve that we have computed before, but in this case, we start from the steady state distribution. And we can see that this was also evident from the previous plot. We can see that the steady state actually is reached in a few number of hyper periods, which I would say that was something that we expected before performing the experiments. Actually, what could not take for granted was the accuracy of this kind of approach. Of course, we know that the microscopic model of tram traffic is accurate, but we could not know in principle what could be the accuracy induced by the macroscopic model of car traffic. And so we performed a validation of the approach with respect to a microscopic traffic simulator. In particular, we used the simulation of Urban Mobility Tool, SUMO. We consider 27 scenarios, which arise considering different values of the street length, the car arrival rate, and the maximum car speed. And we performed a large number of runs for each of these scenarios. We computed the expected number of queued cars, both through our approach and both through this ground truth obtained by simulation. And we compared the obtained results using the normalized root mean square deviation. So the root mean square deviation is I would say, standard measure to compare quantitative measures. In this case, we use a normalized version of this measure because to facilitate the comparison among models that have different scale, because considering street length comprised between 50 and 450 meters means that the queue size may vary nearly between 10 and 100 cars. So we have cases with different scale. In the end, the results of this validation were good, because the approach achieves an error that is acceptable for the context of use, and it is also able to achieve this in time that is more or less one order of magnitude lower than the time needed by simulation to achieve comparable error. Here we have some plots that show the general trend that we have. In particular, we can see that in the cases where we have low arrival rate, then the MMKK model tends to underestimate the expected number of queued cars, and this is mainly due to the fact that the multiple server semantics is not able to accurately capture the single vehicle dynamics, of course. This trend goes in the opposite direction when the car arrival rate is larger. So in this case, we have that the MMKK model tends to overestimate the expected number of QR cars over time provided by the ground truth, which is represented in green here. And this is also exacerbated by the fact that the microscopic traffic simulator we have used tends to abort car arrivals when two cars arrive with a very short, too short inter-arrival times. In the other cases, we can see that the MMKK model is able to accurately follow the trend of the ground truth. And in all cases, as we expected, the MMKK model outperforms the MM1K model. And then finally, to conclude, I would like to mention how the approach can be used to perform what-if analysis and support use cases of interest for operation and management of multimodal intersections. So first of all, combining transient and steady state analysis enables the evaluation of the expected number of QR cars for time intervals having arbitrary duration. So for instance, in this case here, we consider the span of 10 hours during the day, and we consider variable parameters for the tram arrival rate and for the tram arrival period and for the car arrival rate. So we assume that the queue is empty, that the number of QR cars is 0 at the initial time, which is 5 o'clock in the morning. And then we can perform transient analysis starting from the empty queue. We reach a steady state that is the starting point of the analysis with the subsequent values of parameters, with the parameters of the subsequent time slot during the day. And so we can perform this over time for how many time slots we want, using whatever parameters we want. We can also use the approach to select a convenient schedule for car semaphores. For instance, in this case, we consider two car flows that have different arrival rates, one significantly larger than the other. So in the middle figure, we have reported the expected number of QR cars of the two flows, assuming that the hyper period is assigned in this way. So in particular, we have that the two car flows have in principle the same duration of green and red intervals. And of course, except for when the tram arrives, in those cases, the car semaphores are turned red, of course. And so in this case, the duration of the green intervals, and so also of the red intervals, is quite long. So it is slightly less than 1 minute. And so we can see that the expected number of QR cars reaches significant peaks for especially for the car flow that has larger arrival rate. So in the bottom figure, we have a different schedule where we divide in a different way the hyper period. And so we assign the two car flows shorter green intervals. And so in doing this, we reduce the duration of the red intervals for both the car flows. And so this permits to reduce the number of reduce the value of the peaks achieved obtained by the expected number of queued cars over time. So with respect to the previous example, we have lower peaks, and so of course higher, larger troughs. Finally, we could also exploit this to select to select a convenient phase for tram tracks. So in this case here, we have a bidirectional tram line, and we assume that the phase of the first track is equal to 0, and we experiment with 2 different values of the phase of the second track. So in the first case, the 2 trams, which is the first case is the one with the non-dashed line. In this case here, the trams of the 2 tracks tend to occupy the intersection during the same time intervals. And so this means that the duration of red intervals for the car flows is larger than in the second case, where we try to displace the tram passages of the two tracks. And so in the second case, which is represented by the dashed line, we are able to reduce the expected number of queued cars over time, also reducing the maximum peak that can be achieved. So overall, to summarize, I have presented an approach to performance evaluation of multimodal urban intersection, and this approach was the occasion to discuss how model-driven engineering methods and practices facilitate the generation of stochastic models that meet the requirements of the industrial practice, because they are generated from high-level specifications characterized by domain-specific meta models, and at the same time guarantee that these stochastic models can be efficiently analyzed. The specific approach that we have presented is also open to various extensions that we are currently working on. In particular, we are working on evaluating other quantitative measures of interest, such as expected waiting times at the intersection, joint evaluation of of the performance of multiple intersection, and also exploitation in other non-transportation related systems, because in the end, this is an approach that can be used when you have some subsystem that has priority over the available resources with respect to another subsystem, another component. So thanks for your attention.
So thanks, Laura, for an interesting talk. We have time for a few questions. I see a question on Slack channel, so if you want, you can answer in Slack. And please, raise your Samuel, please. I see Samuel back. Samuel?
I'm sorry, I was just clapping. I wasn't raising my hand.
Okay. The other questions? I see a question from Andre, Vittorio, and Murray on Slack. Would you like to ask in person?
Yeah, I can. Can you hear me?
Yeah. Yep. Please.
Ciao, Laura. Thank you
ciao.
for the nice talk. No, I was. That's very interesting, and I think the cases you are considering are very timely and. And nowadays with these systems, we do need this analysis. I only have a curiosity about the tool, the ORIS tool that you were mentioning, and you have mentioned that you have the possibility of doing interactive simulation. And what do you mean by interactive? What's the role of the user? I mean, how the user can possibly act on the simulation at the simulation time, or it's just a question of configuring the simulation before and then going?
So this is, I mean, our simulator lets the user select the next event, event by event. So you can, this is a kind of debugger, I would say. So this is simulating the execution of a stochastic time Petri net event after event. So the user can select the next event, and then the time of the next event is sampled by the system, by the tool, from the distribution associated with that event. The user can also define a number of events and then let the system, I mean, advance the evolution for that number of events. So in the end, this kind of, I would say, token game is useful in the initial stages of design, just to see whether you have placed the tokens in the places where they are expected to be, and so on, just to check whether the model is what you intended to have.
Yeah, it's more for debugging, you would say. I mean.
Yeah, it's more for debugging. Then if you want to, when we have to perform, for instance, a simulation of a stochastic model to obtain a ground truth, then typically we do this in a programmatic approach. So we export the model into a Java code, and we write a Java program that builds the model, launches the simulation, and we run the simulation offline on a server, not in an interactive manner.
Okay, thank you.
Thank you.
Thanks. Other questions?
Well, I could ask my questions.
Yeah, please.
Laura, yes, thank you for the talk. I have a couple of very detailed questions about the model. I've thought about queuing models and traffic, and one of the things that I thought made queuing models maybe not work very well is that you can't model, it's hard to model the acceleration of the vehicles away from, after a red light. And you seem to be assuming a constant speed, that the vehicles are immediately running at 30 or 70 kilometers an hour when the light turns green, rather than having a gradual acceleration away from the stop position. And actually that would make quite a difference. Certainly sitting observing people starting at a red light, it does, or when a light turns green. I assume the simulation model does this, that it moves the cars a little bit at a time with acceleration included.
Sorry, I lost you at a certain point, so I don't know whether I correctly catch your question. So if I understand well, the question is about, I mean, how we perform the comparison of the finite capacity queues modeling the car flows using the microscopic traffic simulator. Is this correct?
It's particularly the assumption of the movement of the cars when the light turns green. The assumption, the Markov model of the queue must assume that they move at full speed.
Yeah, so of course, if I understand well, yes, you are right. So of course, using a finite capacity queue, we cannot accurately represent the actual movement, of cars that we have when we have this alternating green and red intervals of the car semaphores, of course. The point in this case is that we could have a microscopic model non-Markovian model also for the car flows. And this model could be very accurate in representing the kind of phenomena that you are mentioning. And actually, this was the model which we started from in a previous publication when we started working on this topic. The problem in that case is that if we have a microscopic model of car traffic, of course the complexity of the model makes the approach not scalable with respect to the queue size. So another step that we did to still have something non-Markovian in the model, to still use the non-Markovian temporal parameters to model the car flows, was to have I would say, a mesoscale model. So not a microscopic model and not a macroscopic model. So consider different classes and slots for the queue sides. And so, for instance, considering the state where the number of cars is comprised between 0 and 10, 10 and 20, 20 and 30, and so on. But
okay.
Still, this approach still encodes the complexity of the analysis. And in the end, what we obtained was a quite rough estimate. So it is in the end we resorted to the model, to this Markovian model, to represent the car arrivals. In some recent experiments that we are performing, we are also considering the possibility to extend the microscopic model of car traffic, of tram traffic, to measure how many time has passed since the semaphore has turned green. And so we could use this quantitative measure to modulate in a different manner the server availability of the queue model. And so we are, but this is actually still ongoing. That the first results that we have obtained are not so encouraging, but I think we will continue working on this. And if I have understood correctly your question, these experiments that we are doing are in the direction that you were mentioning.
Thank you.
Thanks.
Okay, thanks again, Laura, for your talk. Interesting talk. There are a few more questions in a Slack channel.
Yeah.
So
I will go there.
Okay, thank you.
Thanks.
And now we have the first full paper presentation. Samuel Beck from the University of Stuttgart will present the paper, How is transient behavior addressed in practice? Insights from a series of expert interviews. So Samuel.
Yes, thank you. Let me share my screen. So I hope you can see something.
Yeah, I can see your slides.
Great, thank you. All right, yes, I'm Samuel Beck from the University of Stuttgart, and today I'm presenting joint work with Sebastian Frank, Alireza Hakamian, and Andre van Horn. We gathered some insights from a series of expert interviews on the question of how transient behavior is addressed in practice. First, let me motivate why we conducted those interviews. Modern microservices, to uphold their quality of service is a pretty challenging task because service degradations can have quite enormous downsides, can cause quite enormous costs, as you can see from these two headlines over here. And to mitigate that risk, stakeholders define quality attributes in non-functional requirements and later, during runtime, assess whether they are fulfilled or not. However, in modern software systems, that can be challenging because they constantly experience changes from continuous deployments, failures, or through self-adaptation, for example, because of load balancing or because of resilience mechanisms. These changes mean that a software system is constantly exhibiting a state called transient behavior, which is the behavior while after a change, while the system transitions from one steady state to another. And because this happens frequently, a behavior is quite often in this, a system is quite often in the state of transient behavior. What is why we think that this transient behavior should also be specified in non-functional requirements and accordingly also be assessed whether these requirements are fulfilled. However, not much is known about how this is handled in practice, which is one of the motivations for our interviews. To be a little bit more concrete, what we wanted to do is to build a prototype to improve the current situation for specifying and analyzing transient behavior by utilizing novel HCI interfaces, because they have been employed in other for other problems in software engineering quite successfully. However, for the prototype, we needed use cases and requirements, and there was not much literature out there on these topics. So we thought, why not just go into industry and ask the experts themselves? So the goals of our interviews were to understand how transient behavior is handled in practice, to uncover challenges and problems that practitioners face with it, to identify which tools and methods they are employing at the moment right now for those tasks and to see how they can be improved upon, and to collect requirements that they have for a novel solution. The method that we applied for that was we conducted 5 semi-structured interviews with seasoned software architects. Each of them lasted for around 1 hour, and we prepared 18 questions. However, the semi-structured nature of the interviews gave us some flexibility to also dig deeper into interesting topics that came up during the interviews. The interviews were conducted remotely via WebEx thanks to the pandemic, and as a result, we created 68 pages of transcripts. The structure that we followed during the interviews was we began with general questions about the interviewees' backgrounds. Then we continued with their familiarity with transient behavior and moved on to their current situation regarding the specification and analysis of transient behavior and the challenges that they see with these 2 tasks, and finished with the tools and methods that they employ at the moment and the requirements that they have for a new solution, and also their thoughts on novel HCI interfaces. To analyze our results, our answers, we categorized the answers following that structure, and then summarize the statements from each interviewee for each of those categories. And then in the end, consolidated all of these summaries into one report. The 5 interviewees that we spoke to were all senior software architects at German IT consulting companies that were all working in the enterprise application domain. The first of them was Stefan Tilkoff, who's the managing director and principal consultant at InnoQ Germany. We also talked with Uwe Friedrichsen, who is the chief technical officer at Codecentric, where he's also a senior software architect and responsible for the company's technological strategy. We also talked with Fabian Keller, who is head of cloud innovation at Mimacom and also a software engineer and software architect there. And we also interviewed Matthias Häusler, who's senior managing consultant at Novatec Consulting and has been working at IBM for 17 years before that, and is also ambassador for Cloud Foundry. Our last interviewee could not obtain permission from his organization to publish his identity. So for the matter of this talk, we will call him Thorsten. He works at a major IT consulting company in Germany that mostly develops text consulting software, and is a software architect there. And he also has a PhD in computer science and wrote his dissertation about software performance engineering. That brings me to the results that we gathered during our interviews. Before we conducted them, we stated some hypotheses, and during the talk, I will kind of discuss those hypotheses and whether or not we can reject or confirm them as far as that is possible with the small sample size. The first hypothesis was that engineers are familiar with transient behavior, and during our interviews, we uncovered that 3 out of the 5 interviewees were familiar with the term before the interview or had at least heard about it, but only one of them was really deeply familiar with the concept and its causes. So we can probably say that this first hypothesis is probably not true. We also asked them about the causes for transient behavior that they experience in their systems. And all 5 of them claimed that the most common cause for transient behavior are deployments, followed by failures and resilience mechanisms, although these happen much less frequently than deployments. However, the consequences of transient behavior introduced by them is much more severe. Which also brings me to an insight that we made about which kind of transient behavior is easier to handle or is preferred. And that would be our interviewees prefer frequent low impact transient behavior like that introduced by continuous deployments over infrequent high impact transient behavior, for example, introduced by traditional deployments that only happen once or twice a year, but really have a lot of potential for creating a lot of failures. With respect to analyzing transient behavior, currently only at one organization of those 5 that we talked to, engineers are analyzing transient behavior frequently, and 3 of the interviewees stated that they believe the engineers would be able to understand and analyze transient behavior if they had to. Some of the interviewees also talked about testing before production, and they mentioned that their test scenarios usually do not cover transient behavior because of the complexity of those scenarios and because of the effort that it would be required to create a test setup. However, they believe that scenarios for testing should cover transient behavior as well. So that would be an interesting research direction maybe to look into in the future. So our second hypothesis, that engineers understand the transient behavior in their systems can't probably be answered with that, because it really depends on the kind of system that they're working on and on the priorities that their organization has. With regards to the challenges that I see in analyzing transient behavior, the first is that simultaneous transient behaviors can occur in a microservice system that can affect each other and cascade from one service to another. And these simultaneous behaviors are very challenging to understand and to analyze. Another is that all 5 of them claimed that they already collect a large amount of APM data. However, that amount is so large that the analysis of it is quite difficult and very time consuming. And because they consider transient behavior as not very critical in their domain of enterprise applications, they often don't conduct this analysis. That brings me to some insights that we gained about APM tools in general through our interviews, and that is that better analytical solutions are needed for analyzing large amounts of data. For example, some of our interviewees asked for filtering options and notifications about incidents to make it easier for engineers to learn about incidents that are actually relevant for them and not have to look for them. And they also want easier to understand visualizations of complex scenarios. So to summarize, in order to warrant the analysis of transient behavior, we need to reduce the effort that it takes to undertake that analysis. For the specification of transient behavior, we made a hypothesis that engineers think that transient behavior should be specified in non-functional requirements. However, during our interviews, we uncovered that only 1 out of the 5 candidates thinks that this is the case and that it should be specified in general. The others thought that for their enterprise applications, it is mostly unnecessary. However, they also mentioned that they believe for more critical types of systems, it is probably valid to do a risk assessment and then based on that decide whether or not some aspects of transient behavior should be specified. So the next hypothesis, that engineers actually do specify transient behavior, is quite easy to answer based on that. That's mainly not the case. Again, only one interviewee said that in his organizations, the engineers do specify some aspects of transient behavior in quality scenarios explicitly, and the others stated that they do not specify requirements for transient behavior. However, some other quality scenarios for other quality attributes also kind of implicitly influence transient behavior. When we asked them about the challenges that they see for specifying transient behavior, all 5 of them stressed a lot that the specification of non-functional requirements in general has the challenge that business stakeholders often lack awareness and understanding of the topic. So for transient behavior, what they don't know about is what transient behavior is, what its consequences are, and why it should be specified. It's often not easy for them to understand the trade-off between the costs caused by unspecified transient behavior and higher development costs that would be involved with specifying it and improving the system. And also it is difficult for them to quantify the requirements that they have. And some interviewees stated that often that is something that they have to do actually. Further challenges that I mentioned were defining a response measure for transient behavior, because it is not clear what the desired behavior during or after a change is. For that, you need to ask business stakeholders again, which brings me to the previous point. And another challenge was how to verify that the quality scenario actually captures all aspects of a transient behavior. So we can say that eliciting non-functional requirements is a challenging task in general. And our interviewees stated that they would already be happy if that works well with more easier to understand quality attributes. So transient behavior is really only an afterthought at the moment for them. When we asked them about the tools and methods that they use for analysis of transient behavior or of the APM data in general, they answered that all 5 of them do record APM data at the moment, but they don't have a fixed tool set for working with that data. Often the tools are given by their customers. And at least one of the interviewees, Thorsten, mentioned that tooling is one of the biggest problems that they face when analyzing APM data. He complained mostly that they don't have adequate filters and that their tools are lacking notifications for relevant events. And something else that our interviewees mentioned to us is that reproducing and testing scenarios that involve transient behavior is very challenging with the current tools that they have. When we asked them about their tools for specifying non-functional requirements, they said that in their opinion, communication with non-technical stakeholders is much more important than the tooling that they use. And that's also why they prefer very simple tools over feature-rich tools that are also easy for use for non-technical stakeholders. And what is important for them is that requirements are very easy to capture and also to change. So they mostly use just text-based processors like Word, or even just Post-it notes to collect requirements. So our 5th hypothesis, that engineers are satisfied with currently existing methods and processes for these tasks, are kind of mixed, because some of them, like Uwe, were quite satisfied with the tools they have at their proposal right now. And some others, like Thorsten, for example, think that there's still a lot of improvement needed on that front. When we asked them about the requirements that they have for a new solution that improves upon the state of the art, they all agreed that collaboration is a very important requirement for these kinds of tools, which confirmed our hypothesis that said that engineers collaborate when they assess or specify requirements for transient behavior. They also stated that filtering, as I said before, of incidents, but also of specifications, is a requirement that they have. They want easy to understand visualizations of complex behaviors and scenarios, and also integratability of a solution into the existing environments that they use is quite important for adaptation in the industry. And for the same reason, such a tool should create visible value for business stakeholders. Also, they said it is important that such a solution has a good trade-off between configurability for expert users and usability for business stakeholders. When we asked them what they think about novel HCI interfaces and a solution that incorporates those, they mostly responded that they believe that usable and mostly understandable models and visualizations for transient behavior are still missing at the moment. So for them, the first priority is to develop those models and visualizations before going the next step and thinking about how to incorporate them in these novel HCI interfaces like AR or VR headsets or touch screens or voice assistants or something like that. Also, they feared that a solution that uses these new devices would find less adoption in industry because they're not very widespread at the moment. Something else that we learned is that that bots and chatbots are already quite frequently used in software engineering. So that would be an HCI interface that might be viable for a solution that could support novice developers as well. Based on these results that we gathered, we developed 2 follow-up prototypes. The first one that I want to present today is Transvis, which we also presented at last year's Swissoft. It is a tool that is supposed to support engineers and architects in specifying, finding, and assessing transient behavior in a microservice system. For that purpose, it uses visualizations and a chatbot, as you can see over here in the screenshot. It sports an architecture visualization on top that gives an overview over the system services and also highlights systems that might have a requirement violation. On the bottom, it has 2 visualizations for transient behavior and the loss of resilience of a microservice that show the actual quality of service of a service, but also the specification, the transient behavior specification, represented by this red line to easily make a comparison between the 2 possible. And on the bottom right, you can also see a chatbot window that can be used to create specifications, for example, and which should make it easier for novice developers to interact with the tool. We conducted a user study to evaluate Transvis, and we found out that it is well suited for specification and exploration of transient behavior, and that especially the visualizations are helpful. However, the chatbot is not very useful in its current form and needs some improvement. And the participants were missing overviews and filters for specifications and also incidents. The other follow-up prototype that we developed is Resirio, which is a tool meant for making the elicitation of resilience scenarios more accessible for non-experts and also accelerating this whole process through automation. To that end, it automatically extracts a software architecture from a system through tracing and then conducts a JASOP-based hazard analysis and presents the outcomes of that in a user interface, where the user can again use a chatbot that guides him or her through multiple steps to elicit a resilience scenario. It also shows an architecture graph to give an overview of the system and the outcome of the hazard analysis. And it sports a management component where you can see the configuration of the tool and also the defined scenarios after you have created them. An evaluation of Resirio showed that it's a good foundation for novice engineers to create, to elicit resilient scenarios, and it complements traditional approach as well. That brings me to my conclusion. I've presented 5 interviews that we held with software architects about transient behavior. We found out with regards to specification that transient behavior is only seldomly specified at the moment. Reasons for that are a lack of knowledge from stakeholders and a perceived low priority of transient behavior. With regards to analysis, there's better tooling needed for analysis, especially filtering of incidents is something that is missing at the moment. And then there's a need for better visualizations and models. I've shown 2 prototypes that we developed as a result, Transvis and Resirio. And future work that would be interesting is to investigate transient behavior in other domains than enterprise applications, for example, like streaming, to improve our prototypes based on the results we got from the 2 studies. For example, my co-authors are working on the interactive transformation of ATOM-based resilience scenarios into more formal definitions at the moment. If you're interested in this work, you can check our GitHub page or the supplementary material that contains the transcripts. And I would also recommend you to attend Andres' keynote later today at the LTB workshop, where he will talk more about resilience testing and engineering of microservice systems. Thank you for your attention, and I'm looking forward to your questions.
Thanks, Samuel, for your interesting talk. Other questions? I see a question. Oh, please, Andre, please.
Thank you, Daniela. Very, very interesting talk. I have a question about whether the whether the people you interviewed were actually using performance requirements in the first place, because in my experience, they're usually missing.
Mm-hmm. Yes, indeed they do. At least I believe most of them stated that. But you also have to keep in mind that they usually work at IT consulting companies, and all of them stated that it is usually very difficult to get these performance requirements from their customers in general. And they also stated, for example, that in some cases, they basically have to come up with those requirements on their own and then kind of experiment and see what the customer would be happy with, because it's very difficult for the customers to come up with those requirements on their own and also to quantify them, because the customer, of course, always wants a system that is as fast as possible and that is always available, but it's very difficult to achieve. And so it's difficult to get realistic numbers from them.
That's been my experience exactly.
Mm-hmm.
Then my next question is, did the consultants or their customers realize that transient behavior can implicitly be captured in performance testing, such as stress testing, or by looking at the ramp-ups that occur in performance testing? And what kind of experience did they have with that?
Mm-hmm. That is a very good question. We didn't talk about performance testing in general. Some of them mentioned that they think instead of analyzing transient behavior in production, it would make a lot more sense to test it before deployment. But we didn't talk about performance testing in general. However, what they said is that they believe it's probably very difficult to test scenarios like deployments or failures before production, because it requires quite a big setup, and those scenarios can be quite complicated.
Uh-huh. Oh, so their results are very heavily dependent on the nature of the failure or the nature of the degradation that they're going to see, which suggests to me that they're not thinking about how the system could be degraded and what they could do to prevent it.
Yes. I think they're thinking about it often, at least some of them. I think Stefan explicitly also mentioned, for example, that they often can't test all of the scenarios that they think about. So sometimes they just walk through the scenarios in theory to figure out if that's something that could affect them, and if yes, if they need to define requirements for these scenarios. But yes, it is a very interesting point that you make.
Thank you. Very nice talk.
Thank you.
Thank you. Samuel, there are more questions in the Slack channel, so please, you can.
Well, I could ask.
Oh yes, please, Mari, please.
My question is about the interaction between the applications and the auto-scaling infrastructure in a system which is meant to manage transients in a sense. And so the specifications need to be about the combination of the software system and the management infrastructure that will be controlling it when it's running. And that seemed to be missing from your thinking on this. I wondered, you need to think about what kind of things the software might do how they would affect the scaling infrastructure in order to understand the transient behavior.
Yes, I would agree that the transient behavior is not only influenced by the system itself or by the code, but also from the whole infrastructure, the whole environment surrounding it. I think you're absolutely right in that point.
I mean, a lot of software engineers think that they don't need to worry about performance anymore because the infrastructure handles that for them. So they don't need performance requirements and transient management requirements because that's all done, apart from things like the disasters in the software that fail and then cascade and so on. But
and how mistaken they are, because they're not taking into account the metered costs of using a cloud service.
Oh, well, economic factors are another thing. Yeah.
This is actually quite an interesting point. It reminds me about one remark that one of our interviewers made. He said, we don't really need to specify transient behavior or analyze it, because it is actually just easier if there's, for example, a failure in one of our service instances, to shut it instance down and start 1 or 2 new instances. He said that's just easier than to think about a transient behavior.
But then there's a transient associated with that. But it's not a property of their software system, it's a property of the management system. So
Yes.
in some ways, you need to be analyzing the management system that does the restart in order to see what the transient effect will be and whether that's acceptable.
Yes, I think that is a very good point. Thank you.
So thanks again, Samuel, for your interesting talk. Martina, are you there?
Yeah, I'm there.
Yeah.
Okay.
Can you share your screen?
Yeah, I'm trying to.
Okay. Martina from the FSI Research Center for Information Technology will talk about design time performability optimization of runtime adaptation strategies. So, Martina, the floor is yours.
Thank you. On behalf of my colleague Max Scherer and my supervisor, Professor Ralf Reusner, I warmly welcome you to our presentation on design time performability optimization of runtime adaptation strategies. My name is Martina Rapp, and I'm a scientific researcher and PhD student at the FZI Research Center for Information Technology in Karlsruhe, Germany. In this presentation, we will focus on self-adaptive software systems that follow the MAPE-K paradigm and architectural self-adaptation using rule-based adaptation strategies. Now I have to check whether my slides move forward. Hang on. Okay. It hangs somehow, sorry. Why does this not move? Okay, now it's moving. Okay, sorry. So what is our motivation? Our motivation is to reduce the complexity of runtime decisions at design time. Using model-based analysis techniques to optimize adaptation strategies at design time is our vision. So self-adaptive software systems are faced at runtime with various uncertainties, for example, varying workload and different kinds of failures like hardware, software, or network failures. And in order to maintain their quality objective goals, these self-adaptive software systems for sure adapt themselves based on well-defined adaptation strategies to changes that are occurring at runtime. Now, the designing adaptation strategies which ensure the continuous operation in these uncertain scenarios, even in the presence of faults, is from our perspective a key aspect of self-adaptive systems. We see the challenge that the permanent change of the system's configuration over time makes adaptation strategies inherently hard to analyze and also optimize at design time. And generally, this problem is addressed at runtime, where uncertainties are resolved by collecting runtime data. But for sure, it's also desirable to be able to make architectural decisions for adaptation strategies at design time. So we think that design time analysis and optimization helps to explore and identify possible candidates of adaptation strategies. And in contrast to the general approach, our design time strategies have an optimized runtime behavior by identifying promising adaptation strategy candidates in advance. And we think that this results in an increased runtime convergence behavior of the adaptation strategies. So let's first have a look at the current state of the art. Our review looked at 3 main topics. The first topic was languages and tools for specifying adaptation strategies, with a special focus on available domain-specific languages that are applicable for runtime and also design time modeling. The second topic was performability analysis and modeling of dynamically reconfigurable component-based systems. And the third topic was approaches for optimization of adaptation strategies. And in particular, we looked at classic optimization approaches and also at machine learning approaches. For the complete list, I would like to refer you to the respective section in our paper due to timing constraints today. So this brings me now to our identified research gap. Our review showed that existing approaches lack support of design time analysis to optimize runtime adaptation strategies. Reasons are that no domain-specific languages are available to describe the adaptation strategies, including their inherent set of rules. Also, there is no performability-based evaluation approach for these adaptation strategies, which makes the evaluation of the effectiveness of such strategies in case of failures difficult. And finally, there's also no approach to optimize these adaptation strategies in terms of an optimal parameter set. Therefore, we see the following challenges. First would be identify the missing required elements for optimization. Here we see especially parameters, set of rules, and maybe more. Second, the performability evaluation could be a possible starting point to evaluate these adaptation strategies. And the third challenge we see is that optimized adaptation strategies is good in order to design resilient software systems by preventing system degradation through the design of effective adaptation strategies. So this will bring me now to our vision. Our vision is to use model-based analysis to optimize adaptation strategies at design time. On this slide, you can see an overview of the involved parts. In order to investigate the adaptation strategies at design time, one thing you need is an abstract system representation of the self-adaptive system. Once you have such an abstract system representation, you are then able to use model-based quality analysis techniques in order to explore them. As I already said, this enables you to explore various architectural design decisions, and very important, you can do this together with their impact on the system's quality attributes. While considering these effects of the adaptation strategies on the system quality attributes, software architects are then able or can come up with well-founded design decisions and thus improve the overall system quality. Therefore, our vision on the design time performability optimization includes the following points. Point number one would be to have a DSL to represent adaptation strategies and the MAPE-K loop in an abstract way. If you have such a DSL, user at design time would then be able, this user is usually a software architect, to create a MAPE-K and adaptation strategy model of his or her future system. And with this model can then be used as input to an analysis tool that carries out the actual optimization of the adaptation strategy. So in the next slides, we will look more closely on the requirements and challenges for such an DSL and its meta model, and also on the optimization approach. To illustrate our vision, we use the well-known CNN example. And on this figure shows different Palladio model views of this ZNN example. And on the left-hand side, you can see the model of the user workload. On the top, you can see the probabilistic load balancer behavior. And on the bottom right, you see the deployment view. When you are now looking at the performability requirements, they include mainly two factors that can degrade the system performance. One is the overload scenarios due to high workloads. And the second one are hardware failures, like, for example, failing application server nodes. A typical adaptation strategy for this scenario now would include the handling of the load distribution and also the handling of unavailable nodes. And this corresponds to the points 1 to 3 on the slide. So the interesting questions in this setting are now, what is the role of the DSL? And also, what is the role of the optimization process, which corresponds to points 4 and 5? To answer the question about the DSL enables the definition of the adaptation strategy by modeling the required rules and also actions that should be taken. In contrast, regarding the optimization process, the parameter optimization process now finds the optimal setting that guarantees that the system quality objectives are met best over time. So now let's have a closer look at the known requirements we see for our envisioned meta model. Requirement number 1 would be that it must address runtime adaptations at design time. It also must allow the modeling of a MAPE-K loop. It also must allow the modeling of sets of rules and control structures together with their properties. And last but not least, it must allow the modeling of actions with variable parameters. In this setting, as open questions and open challenges, we see the following questions. Question number 1 would be how to model actions with the variable parameters. Question number 2 would be what kind of uncertainties are relevant at design time? And question number 3 would be how to handle those relevant uncertainties at design time. And as a possible solution, we now see a domain-specific language based on a meta model. On this slide, we have a first version for such a meta model. Our unified MAPE-K meta model represents, as I already said, the MAPE-K loop and the adaptation strategy. The meta model is organized into the following subpackages, which are the monitor subpackage. This one defines the available monitors and metrics used to observe the system properties by collecting runtime data. The analyze part contains the set of rules to evaluate the collected monitor data. In the planning part, this defines the set of rules and actions which are specified as model transformations, usually by dedicated domain experts. The execute part contains the selected set of rules and actions with a then fixed parameter set that should be later executed. The knowledge part contains the current system state and also the knowledge about the variability points in form of a variability meta model. Let me say some details about this variability meta model. This model defines the potential parameters that can be varied within an adaptation strategy and is especially important for the optimization part later on. The set of rules now contains the if then else rules that are referenced during the analyze and planning phase of the MAPE-K loop. I will now briefly go into the topic of set of rules and control structure representation. In our view, the abstract conditions represents the states of the system properties. Abstract actions describe the structural and behavioral modifications that a system must carry out to comply with its quality objectives. Also, these actions define individual modification steps as abstract parameterized operations. And a quick note on the side, the actual execution of the roles is for sure done in the execution phase of the MAPE-K loop. And usually it's done in some kind of QVTO transformations. So what is action parameterization using variability in this setting? We believe that parameterization variability of actions is key to optimize because it encodes the system's variability points. So therefore, the key points of our planned variability beta model are the types of the action parameters, the degree of freedoms of the action parameters, the changeable structural part of the system, but also the adaptable behavioral part of the system. And we see the variability meta model as part of the knowledge part in our overall meta model. Usually this variability meta model is referenced during the planning phase in order to determine the concrete adaptations that should be taken on later. To make this more illustrative, we have here an example to better illustrate the idea of the action parameterization using this variability. So let's assume that we have the following two abstract actions. Action number 1, called add component, encodes a structural change by adding new components. So the action contains as variability points the component type, which references the component type that should be created, and the number of instances that should be created. Example number 2, change component attribute. This now encodes a behavioral adaptation by changing an attribute value of a component instance. In this case, it would set the distribution factor of the previously mentioned load balancer component to a new value. So next, I would like also to go into the topic of modeling uncertainties. We think that to optimize adaptation strategies at design time, only a subset of uncertainties must be considered. The subset depends on the system concerns under study. And in case of the performability domain, we see that these are mainly the triggering factors that impact the workload and the failure types of interest. So therefore, we see the following challenges. To identify relevant uncertainties of the performability domain, also to identify design time relevant uncertainties. Next, also identify optimization relevant uncertainties. And last but not least, for sure, identify a reasonable abstraction for the relevant uncertainties. And also a very important question is how to consider uncertainties during optimization. And here I would therefore be very interested to learn your opinions in the upcoming discussion. And I also would greatly welcome your input on this topic because we think that it's a very crucial topic in the whole setting. So let me conclude this section on our envisioned meta model by having a very quick look at the current state of our unified MAPE-K loop meta model. It currently includes the following main components, which are the MAPE-K loop, the set of rules, and the variability part. This part is roughly sketched at the moment as the knowledge data in the figure. To be more clear, all parts that are colored in blue, they refer to the actual MAPE-K phases, and all parts colored in yellow, they refer to the data that must be evaluated within each phase. Okay, so now the DSL topic is almost done. Let's switch over to the optimization part of the talk. Let's take a look at optimizing adaptation strategies at design time. The optimization at design time is challenging because of several reasons. One reason is that usually not all possible extrinsic events in the environment are known at design time, like, for example, varying workloads or system restarts due to a virus or something else. The case of intrinsic events on the system is a little bit different because they are known, but here's the challenge to simulate them at design time, like, for example, resource failures. Another challenge that we see here is that the monitoring of quality attributes might not be available at design time, which also might require some estimated guesses. So our vision is to reduce these challenges by enabling the development of adaptation strategies, optimization at design time, so that they are tolerant to disruptive events. Our optimization goal is now to select the best candidate of an adaptation strategy with its optimal parameterization. Our optimization candidates are the parameter sets of the adaptation strategies, whereas the inappropriate candidates are parameter sets which violate system quality properties later at runtime. So one challenge we see is how to identify these appropriate sets of candidates. Another interesting question in this context is, to which extent is it possible to identify these candidates at design time? And also, what is the trade-off between design time and runtime optimizations? And last, how much optimization should or actually can be done at design time compared to runtime approaches in order to support the design of these adaptation strategies? On the other hand, we see the following benefits of design time optimization. One benefit could be the exploration of the adaptation space at design time helps to identify these inappropriate adaptation strategies in advance. And this might significantly reduce the adaptation space that needs to be explored later at runtime by identifying a meaningful pre-selected set of adaptation strategies. Also, the runtime optimization approaches usually start their selection process without any previous knowledge. Consequently, finding an optimal strategy takes considerable time in this setting. But starting with a reduced pre-selected adaptation space might shorten the time the system is in an unstable state, because we think that chances are much higher that the adaptation strategy converges faster due to the restricted set of candidates that needs to be explored. Also, it would allow us to reason about the system architecture, about system architectural problems in general at any stage of the development process, as these problems can be directly observable in the model. And this would enable us to investigate the impacts of different adaptation strategies without the restriction of depending on a fully implemented system that might be costly and also time-consuming to change. So this brings me to the end of my presentation on our envisioned design time approach. Thank you for your attention, and I'm very much looking forward to having discussions with you and answer your questions. Thank you.
Thanks, Martina, for your interesting talk. There are questions from both. We have time for a few of them.
This is Vittoria. I posted 2 questions on Slack. Martina, I can formulate them here. First question, thank you for the talk. First question that came to my mind is how general is your meta model, is your language with respect to the modeling notation that one can adopt? You have shown, for example, some Palladio-like models, no, with the different views. So have you designed your meta model with the objective to be applied also to other notations, and how easy it would be to port those adaptation actions in different modeling contexts?
In the first context, it's first set up for the Palladio environment, but we hope that this meta model will be general enough so that it can be also used in different settings. Maybe you need to re-implement the concept, but we really hope that the concept itself does not depend on the Palladio system. Does this answer your question?
Another short question, if I can. and this is about propagating the actions across different views. You have mentioned in one slide that, of course, if I introduce more components in a static view, then I probably need to change something in my behavior. Is this defined? Is this intrinsic in the meta model in the sense that it's a mandatory action? How do you figure out this aspect will be treated and could be, you know, it's modeled in your language?
So we think that modeling the actions itself is independent from our Palladium model. So we see that this meta model is more or less a representation of the managing system itself, whereas the Palladium model is the representation of the managed system. So for sure, you need the domain knowledge of your system under study in order to formulate and define these actions. But they are not connected in a direct manner on a technical level. They should be independent from the Palladio world.
Okay, thank you.
You're welcome.
Thank you. Other questions?
I could ask one,
Yeah,
Danielle.
please, yes, please.
You're proposing to explore the appropriate and inappropriate parameter space by doing quantitative evaluations, is that right, of the application model?
Exactly.
So this is a little bit like an offline optimization study of the, or feasible space study of the application model?
Exactly, yeah.
Looking at all the contingencies about workload, large and small, and so forth.
Exactly.
Okay, that somehow didn't, the details of that didn't come through exactly.
Okay, sorry.
Maybe I missed something. No, yeah. I think it's
okay.
Okay.
It's very interesting. What about parameters of the management system, such as its averaging time, its delays, in order before it makes decisions? I don't think you.
That's exactly the point where we just started. What kind of parameters do we actually need? At the moment, we've started with focusing on the parameters used or needed for the managed system. But as you are right, there will be also some parameters concerning the managing system part. And this would be also something to include in the meta model for sure, because it models the conditions and constraints of your managing system and also should be considered somehow.
Thank you.
You're welcome.
Thank you. Thank you, Martina, for your talk. It's time for a break. We have a short coffee break and we will back in 10 minutes and we will have a presentation from CU Zhu and Mari Wutsai, multi-server approximation for cloud scaling analysis. See you back in a few minutes. Okay.
Hi, Daniele. Are you there?
Yes.
Hi.
Hi.
It's very, and so my co-author, CU, will show the slides, and we'll both talk. I'll start out, and then CU will do the body of the presentation. CU, you want to turn on? Maybe he's taking a break. There he is. Hi, CU. Good.
I see you.
We should say hello to each other before we start presenting.
Okay.
So, Mari, just to let you know that Catalina will be the chair of your session, not me.
That's nice. Okay. Sure. I think it's going very well. I'm enjoying it. Hi, Kathy.
Hi, now I had the microphone off.
Sure.
How are you doing? Are you
Oh,
ready?
very well, thanks. It's fine.
Oh, you
The
look
whole
good.
pandemic thing has been a bit of a bind, but we haven't had too many problems, and we haven't caught the virus yet.
Well, that's good.
Although
I did have it, but I had
Have you?
nothing.
No,
Yeah, but I
more
had
and
just
more
like.
people we know have got it. But however,
Hey, Connie.
Connie,
Hi.
hello.
Hi, good morning. It's very early morning here.
Oh gosh, it must be 6 o'clock, 7 o'clock,
Well, it's
8 o'clock.
it's all the way up to 8 o'clock. Yeah.
Yeah, right. I was almost surprised to see you on there at 6 your time.
Yeah.
I thought, well,
Right. On
I thought-
Sunday.
Connie.
Hey.
Andre,
Hi, Mari.
hi.
Well, this is very interesting. I'm enjoying it.
Yeah, this is a good, some good
Good to
thoughts.
see you all.
I enjoyed the hot cloud workshop yesterday too.
Oh, yes.
It was quite interesting.
Well, it's almost time, so maybe we could start. What do you think?
Sure. Well, see you want to share your screen
Okay.
and set up the presentation.
So, well, let's start the second session of the workshop. We have 2 papers and then our keynote. So let's start with the multi-server approximation for cloud scaling analysis by CU Zhu and Moray Woodside. Please.
Hi. Sorry, Scotty, I didn't mean to cut you off. Welcome to this talk. Let's go ahead to the next slide, CU.
Okay.
This talk is really in the context of model-based management, model-based auto-scaling, for example, of web systems. And as we saw in the last talk, which was on this topic, the management system is a control loop. The service system produces measures which are fed to a decision system on the left in the block diagram here, and decision system then gives instructions to a layer which makes the changes to the system. In model-based management, the search and decision logic is based on a model of the system. And we're thinking in terms of a performance model, which involves a model of the contention for the system. The thinking for this search does. An example of an auto-scaling system based on a model like that is this paper, an autoscaler called Atom, studied by a student of Giuliano's, Giuliano Casale at Imperial College, which used a layered queuing model to search the scaling space and find a better scaling. And the advantage of a model-based autoscaler is that it can look at simultaneous decisions, coordinated decisions across the system. So the problem with model-based decision-making is you have to do a search and you may have to solve the model many times. So fast model solution and robust model solution, very important. And there have been problems in this area. So next slide, see you. So we're talking about particularly microservice systems in which each service is a set of load balanced replicas, which makes it a multi-server. And we're talking microservice systems tend to be quite large, dozens, sometimes up, like 100 is not uncommon in terms of the number of separate services, that is separate multi-servers in the model. So large models and large scale systems in terms of many users, many replicas, this is very challenging for producing predictions from the model. And the time it takes to create a prediction has to be small. It has to be, in fact, in a few seconds in order to do a search and produce a decision within a time of the order of a minute or a few minutes. And that's the time that's necessary because that's about the time it takes some of the control actions to take place. It takes longer to add a server to a system than it takes to subtract it. Adding a server seems to typically take some minutes. So we think in terms of a model solution in a few seconds. So let's, next slide. Good. Here's the example from that paper, the Atom paper. This is an example which is a microservices demonstration system that was created to show how microservices could be created. It's an e-commerce system which sells stockings, stock shop, and it has 6 services, so it's a small system compared to typical commercial microservices systems. Each software multi-server is indicated by a parallelogram here. Each of these software multi-servers has a queue, except for the one at the top, which represents the users. It has a queue, and it makes calls to other microservice operations. This has been modeled slightly from the model that's published in the paper, in that the operations of the services have been merged to give a single class service at each multi-server, because that's the kind of server we're looking at in this paper. Next slide, see. So solving the multi-servers is a problem because of there's a scalability problem. If you use a mean value analysis, you can do an exact solution for a state-dependent rate service, but it requires storing the marginal probabilities at the queues. So it's of the order of n squared, where n is the number of customers, n is the number, yes, n is the number of customers. You have to solve the exact solution. You have to solve the system over and over again as you increase the number of customers from 1 up to the number you have n. So the overall solution complexity is n times for the number of iterations you have to carry out and n for the marginal probabilities. And this, if you have thousands of customers, tens of thousands of customers, becomes prohibitive. Approximate NVA, approximate mean value analysis, has typically manages with less, because it doesn't have to do the iterations. It doesn't lift the population gradually from 1 up to the number. It solves only at the number of n, but it still needs to calculate the marginal probabilities in order to get the throughputs. At least some approximate NVAs do, and some don't. So the solution accuracy depends basically on the shape, how correct the shape of the approximate probability distribution is, because that determines whether it has to wait or not. And if it does have to wait, how long it has to wait. Next slide, see. There isn't an issue with solution times. We have a solver for these layered models, and there are many multi-server options. You can choose the option for each server in the model, and the multi-server options, there's about 6 of them, but 2 of them have been used over time, preferred. One of them is an approximation by Conway from the 80s, which is more accurate, and another one is approximated by Rolia from the 90s, which is faster. The Rolia approximation doesn't require any marginal distribution. And we tried a new approximation, CU's thesis work, which we call AB. And the solution times by LQNS, AB has been implemented in LQNS, and solution time is about 4 times faster than Conway and a bit faster than Rolia. Rolia has a bigger problem. It's been very satisfactory for speed, it's adequate for speed, but it sometimes, in fact, fairly often doesn't converge. And that means we don't have a solution, or not a very accurate solution if it doesn't converge. So the factor of 4 could be important, and the convergence is very important. Next. I think now with CU, we'll talk about the AB approximation.
So the type of the model we are interested in is closed Markovian queue, which has exponential sync time and service time distributions. FIFO discipline with n number of users and m number of servers. The simple queue diagram is to show the flow of the system. Each customer starting at the top circle goes to the queue after the sync time if all servers are busy and waiting for the service getting served, and back to the sync state. The first approximation I'm going to introduce is Rolia-Franks approximation, which is currently used in LQNS solver and has been used for years. It assumes these servers are independent and to estimate the probability that all servers are busy based on this assumption, which is the mth power of the single server utilization. Then it estimates the waiting time by the arrival theorem, which states that a customer arriving at a queue sees the steady state distribution of the same queuing system with one less customer. It's highly scalable as its complexity does not increase with larger systems. This is an example that the mean queue length with one less customer L is estimated by using Bart-Schweitzer proportional estimation, which is this n-1 over n term. And the waiting time calculation is based on the arrival theorem. The RF has defects. One is it does not return 0 mean waiting time when number of customers is smaller than the number of servers. And another one is the convergence problem. It does not guarantee convergence, especially at heavily loaded systems. The single server approximation is pretty straightforward. It treats a set of servers as a single server, but with S over M service time. The service delay is added so customers do not go back to the sync state too quick. The special thing is for the response time. It includes this extra delay. The binomial approximation is an idea from De Souza et Silva and Mons, who used a multinomial distribution for the Q state. And the binomial is a special case of the multinomial. By using the binomial, there is a parameter P, the probability that each customer is at the server. And we use this P to calculate PI, which is the probability that I customers are in the system. And all of these are based on the assumption that customers are independent of each other. And finally, we can calculate the departure rate and the waiting time. However, the results are not ideal. We found the binomial actually works better with the arrival theorem. So we modified the binomial approximation to have this AB approximation. The PI equation now fits the n-1 customer system, and we are using L instead of departure rate for the waiting time. We have a new concept here, the traffic ratio. It's the balance between the maximum departure rate and the maximum arrival rate. We found that the cases with t close to 1 have worse accuracy in all approximations above, and below is the response time constraints. We see that t equals to 1 is near the intersection of the bounds. We also have the relation between the saturation and the traffic ratio. 3 cases, 2 servers, 4 servers, and 8 servers, and all of them reach nearly 80% of saturation when t is 1. This helps us to define the system congestion level for different values of t. A good thing about using t is you don't need to know the solution of the model and still can set the values to t for the experiments. We use relative error for accuracy. The relative error calculation is the difference between the waiting times over the response time. These figures show a quick look at the approximation errors for RF, AB, and SS for a model with the population equals to 100. The traffic ratio takes the value from 0 to 5, and the values for M are shown in the plots. The errors are less than 25% and are mostly concentrated around t equals to 1. For large M, in both SS and RF, the peak error tends towards higher value of t. In AB and SS, the errors coverage, the errors converge towards zero as t increases. For IF with M equals to 70, the error increases above t equals to 3 and takes a value of about 2%. It's notable that in most cases, AB and SS tend to overestimate the waiting time, which gives positive error, while RF tends to underestimate it. The table here shows the errors for these 3 approximations based on the different ranges of traffic ratios. We can see AB is always the most accurate one in orange, except for the mid-range, where SS is slightly better. And notice in the very heavy traffic system, AB is extremely accurate. For the maximum ARE, the results are alike as the mean ARE. AB are close to or slightly worse than the other two in moderate and mid-range, but much better in heavy traffic system. And RF has a severe convergence problem, especially in the systems with large t values. For the histograms, we picked the traffic ratio from 1 to 3 to show, as it's very common for these systems. The x-axis is the errors and the y-axis is the number of cases. The first cells are not shown as the counts are too large, so we put them in as text instead. We have histograms for all t ranges in the paper, and here just to show the shape of each approximation. I will pass time back to the professor outside for the conclusion.
Thanks to you. So in conclusions, we did find something that works a little better. And AB looks pretty satisfactory as a replacement for RF in our solver. We were very interested in this single server approximation because we've seen that being used in web service scaling papers, model-driven scaling papers, that where they think this is just a simple way to get a model with the same total capacity as the multi-server, but quick to solve, analytic solutions, and so forth. But it does have much larger errors for small traffic levels, for small t. And it's actually a little better than AB around t equals 1, which is interesting. So it looks like we probably ought to implement that in LQNS as well, although we haven't. And the one we've been using, RF, has the most problems, which is unfortunate. It's a very scalable approximation, but it's probably better not to use it, especially if you want to do search, automated search over model solutions, which we've been doing for a variety of purposes, not just scaling, but deployment and automated deployment of large systems, up to hundreds of deployable elements. So next slide. I want to come back to model-driven management, which I think is really the important issue here. And maybe why is it not more successful? And I don't think that solution time is the major drawback, although it's something that has perturbed us when we've tried to use it. So we figured we should solve that. But maybe difficulties in learning the model in order to do model-driven management are more serious, and maybe there's some other problems. Anyway, that's our talk. Thank you.
Okay, thank you very much, Murray, and see you. Is there any questions by anyone here? I have a few questions otherwise.
Good for you, Kathy. Go.
I have a question. Perhaps I missed this, but were these studies that you did on the one model that you presented in the beginning, or was it on a set of models?
Oh, good point, Connie. No, the evaluation, the accuracy evaluation that we presented there was on a single multi-server. Just one multi-server with a population. That's the model that CU showed when he started. Now, we did go back and looked at the example. There's something in the paper on this. We went back to look at that 6-task example and compared all the different solutions. And the solvers all gave the same results on that model within 0.01%. The interesting thing there was that they were all wrong around t equals 1. They all had errors, but of course we've seen that already, that there's some errors around t equals 1. So the comparisons were not on a full-size system. They were on a single multi-server. Now we have been doing accuracy comparisons on example systems, and the accuracy comparisons are very consistent with what we see here. It doesn't get worse with more servers. In fact, it typically gets a bit better because you have it averaged in with single servers and other things that are easier to estimate. So in some ways, doing it on an isolated multi-server is a worst case. It's a stress case for the accuracy. Okay.
Thank you. So t equals 1 is essentially at saturation. Is that right?
Not quite. If you look at the utilization, the result curves for utilization against the t value, saturation occurs just above t equals 1, between t equals 1 and 2, depending on the number of servers. In fact, a few cases with just 2 servers, T can be even 3 and the system's not quite saturated. So most of those points are up near the upper boundary of that, that curve where it goes up and then goes straight. But some of them are down below. And T can be larger and the system not be quite saturated. It depends on the balance of think time, time away, and time at the and number of servers. It's a complicated trade-off. But the nice thing about T, an important thing for us, was that you can set it before doing the experiment. So you can plan experiments around T with some confidence that you're governing in traffic intensity. But it doesn't translate precisely into server saturation.
That's great. Thanks for clarifying.
But T equals less than 1 is definitely not quite saturated, as you can see from this graph that CU's put up.
Thank you. I think there are a couple of questions by Giuliano. Giuliano, would you like to do them?
Sure. Hi, Mari. Hi, see you. Thank you for a nice talk. First, a very technical question. In the binomial approximation formula, in the AB approximation, you have a term Q that scales. You have P over Q. What is Q?
Oh, Q is 1 minus P. I'm sorry.
Okay.
Yes, that's a copy,
Sure.
copied from another document.
Clear.
You're right.
And
it's a standard binomial notation.
Do you have a sense if this could generalize also to FCFS with non-exponential, like high variability?
Like hyper-exponential?
Yeah.
This is approximating the Q length distribution rather than, it doesn't approximate the service distribution. So I would say probably. You know, I'm not quite sure how it would work. I haven't thought about it, Giuliano. That's interesting.
Yeah, because you have the residual time as well.
Yeah.
So
no, there's another parameter there, isn't there? The variance parameter.
Yeah.
At the very minimum.
Sure. Thank you.
Yeah.
Very much.
Well, if you look at approximate mean value analysis and how it treats variance of the service time, it mostly comes into the residual life calculation, right?
Right.
And the residual life calculation for multi-servers is very complicated. That's why you don't see it in this presentation, because it's the first services. It's a race between the different services. If the Q is less than n, you have the first. So the model is so complicated that we haven't tried to incorporate it in LQNS for multi-servers, which is another source of inaccuracy, I'm afraid.
Thank you very much for the clarification.
Thanks for the question.
Well, I think that now we can carry on with the next paper. Thank you very much, Murray, and see you. Is there any one of the authors? Okay, I can see you now. So next paper is analysis of garbage collection patterns to extend micro benchmarks for big data workloads. Please, can you share your screen with the presentation?
Hi, hopefully the screen is visible now.
Yes, it is.
Okay, wonderful. So let me just get up. Just to confirm that the presentation screen is visible, right?
Yes, it's fine.
Okay, thank you. So good evening, everyone. I am Ayush, and we have with us Samyak, Aditi, Pranav, Professor Santosh, and Professor Subramaniam. We are here to present our research on analysis of garbage collection patterns to extend micro benchmarks for big data workloads. Or in short, let's talk about some trash. So what is the current state of garbage collection in big data workloads? So the existing Java benchmarks are not specifically designed for big data. Since big data workloads have unique memory patterns compared to most other Java applications, these being huge objects and long-lived shuffle data and so on. They also have some unique computation features, with being CPU-intensive operations and iterative computation. Some of the existing JVM profilers do not provide object-level allocation characteristics. The level of information provided by these tools is not adequate to perform analysis on the lifetime of objects. For example, if we need to figure out if one class of an object allocated in a certain function lives longer than the same object allocated elsewhere, right? This requires individual object data with lifetime, class, and allocation site details. So let's talk about the motivation behind this project, right? The garbage collection can be a significant contributor to latency because of the pause or stop the world events, right? In big data applications, garbage collection can take up a significant portion of the total runtime. In some cases, up to 50% of the time is spent in garbage collection. Comprehensive object analysis using allocation and lifetime data at the object level requires a lot of profiling from the JVM. Although exist a lot of tools that provide GC details, heap space usage, CPU usage, and so on, they lack granularity of data. Object level data can be used to perform lifetime analysis, and with class and allocation site information, one can find the exact line of code where a large amount of objects are being allocated and of which type. So let's go over some of the existing work, what is needed and why is it needed, right? So the existing profilers provide aggregate object data at a given point in time on the heap. Although these tools provide aggregate object data, such as the number of objects alive on each type at a given point in time on the particular heap, it does not include data such as allocation site, allocation time, and lifetime of each particular object. So we explored something called Antrax, which is a modified Java 8 virtual machine, which tracks objects throughout the lifecycle of a Java application. It tracks the birth, the death, and most importantly, the movement of objects through the heap. Big data workloads have a unique memory characteristics, and hence existing garbage collectors are tricky to get right. Concurrent garbage collectors such as CMS and G1 reduce pause time as intended, although resulting in a contention for CPU time, resulting in a lot of inefficiency. Moving on to Samyak.
So what's the solution to this gap in profiling of Java programs? We have built an object analyzer pipeline to extract object level data from any Java program. So for every object, the pipeline provides the lifetime, which is the time difference between when the object was allocated and when it was collected. The type, which is just the class of the object, and the allocation site, which is the line of code where the object was allocated. This information is collected by a modified version of the Antrax JVM, and it's written to highly compressed trace files. The Analyzer app, which was created using Antrax Analyzer, then extracts this information into a Parquet file to make processing easier. This entire pipeline, along with the source code, is open sourced at the link given here. On the left, you can see the pipeline with three of its main stages: the Antrax JVM, the object analyzer, and finally the analysis of the generated data. Now let's get into some details of this pipeline. So one of the many problems we had to solve was associating the life and death of an object from only GC events. We solved this by attaching a unique ID for every object that is created. The lifetime can then be calculated by simply storing a mapping of the tag and the birth time of that object. This raw object data can become quite huge. To control the size on disk and to make processing more faster and more parallel, we store this data as Apache Parquet files. And then we make use of the Dask framework for analysis of this data. To see a pipeline in action, we ran it on some of the Hadoop example programs. These include programs and data of various sizes. And using the results from this pipeline, we implemented a few micro benchmarks to see how certain programming patterns affect performance. And these are the details of the hardware and software setup on which we ran our experiment. Moving on to the results.
Examples we used were calculation of pi via the BBP algorithm and quasi-Monte Carlo. We also, other examples included word count, Sudoku calculation, and TerraSort. Using quasi-Monte Carlo, the value of pi was estimated to a certain precision specified as input. Calculation of pi was also done via the Bailey-Burnian-Plouffe algorithm with an input params of 100k digits and 16 mappers. For word count, we provided a 100 MB text file using for the Sudoku example.
We cannot hear you very well. Is it possible? Maybe if you get closer to the computer or something.
Is it better now?
Yeah, it's a bit better.
Yeah, I'll stop loading. louder. Do I restart?
Now
No, no.
it's a bit better now.
Yeah, so I guess I'll just restart. It's better. So the examples we used were calculation of pi via the BBP algorithm, quasi-Monte Carlo, word count, Sudoku calculation, and TerraSort. Using quasi-Monte Carlo, the value of pi was estimated to a certain precision specified as the input. Calculation of pi was also done via the Bailey-Bourvin-Klug algorithm, also the BBP, with the input parameters of 100k digits as the precision and 16 mappers. For our word count, we provided a 100 MB text file. For the Sudoku example, it uses a unsolved Sudoku puzzle as input and uses the dancing links algorithm to find the solution. For TerraSort, we used a gigabyte binary file as our input. Throughout these examples, we found some classes that were extensively used via our object analyzer. Maps and related classes such as hash maps, concurrent maps, Apache unmodifiable entry set were the common ones. Another finding was that immutable objects led to faster heap fillings and longer lifetimes. This led to the garbage collector, being triggered more often. Here are a couple of visualizations generated by the object analyzer pipeline on a Hadoop example. The first graph shows the mean lifetimes of all classes of objects seen in the program. Note that this only included classes that have more than 1,000 objects. The lifetimes of these vary from 80 to 200 milliseconds. The second graph is the distribution of lifetimes of all objects allocated during the execution of the TerraSort example. It can be observed that most objects have a lifetime between 0 to 500 milliseconds. More such graphs and analysis of our examples can be found in our paper.
So based on the access patterns observed in the Hadoop results, we codified some of the patterns leading to custom JMH benchmarks. And these were implemented having the IONOT benchmarks as a reference. So the benchmarks we implemented were dynamic versus fixed size array allocation. This was added since a significant amount of dynamically allocated lists or collections were being used in the dancing links or the Sudoku example. Using primitive versus box type integers, string concatenation versus implicit string concatenation using implicit string addition versus using string builder. This was considered since a significant amount of implicit string addition is taking place and toString is invoked in the dancing links Sudoku example. And finally, the multiple array benchmark, which compares allocation of multiple small arrays versus a single large array. So byte has a similar mean lifetime in both pre-allocated and dynamically allocated arrays. Byte as the box type has twice the mean lifetime as byte in the primitive type. Since it is referenced by java.lang.byte, which has a longer lifetime, there is a very negligible difference in the runtime performance of using string builder and implicit string addition. The string object when using string builder has a minimum and maximum lifetime greater than when using implicit addition. Finally, for the multiple array benchmark, splitting a large array into multiple smaller arrays adds the overhead of extra padding and reference size bytes for each smaller array. Large array lists last longer, possibly because it uses less memory than smaller arrays, so the heap fills up slower. Object type, on an average, lasts longer in a larger array than a smaller one, possibly since instantiating more objects takes more bytecode instructions. So the takeaways from our work include: pre-allocating a large array does not provide any significant runtime performance benefits. Boxing has a large overhead in runtime performance, and it is best to avoid box types when possible. But the nature of Java generics requires the use of box type in some cases. Arrays scale linearly with the number of elements. Large array lists last longer, possibly because it uses less memory than smaller arrays, and the heap fills up slower. There is a very minor difference in the mean lifetime of objects in string builder and implicit addition. String addition scales linearly with string sizes. String builder is slightly more performant, and this could be possibly attributed to the fact that using implicit additions creates extra objects which fill up the heap faster, triggering more frequent GC, and hence the lifetime of the objects is shorter. Although string builder can be slightly more performant, the convenient syntax of implicit addition makes it the clear choice when applicable. String addition also scales linearly with string sizes. And finally, the most important takeaway of all is that the best time to do a GC is sneaking one in when no one's looking. Thank you. Any questions?
Thank you. Thank you all. Anyone has any question? Well, maybe other people think about it. Just if like Java developer could see your findings, how could, for example, use these findings? What do you think it would be like most important for them?
Aditi, do you want to take that?
I think that while they're developing the application, they could use these takeaways in mind, keep these takeaways in mind. And even when they monitor what they have developed or performance test what they have developed, they kind of can use these metrics, to as a basis to think of when performance testing. Like they can see that, okay, let's monitor how large versus small arrays are doing, boxing is doing. So these provide guidelines as well as a basis on which to think of when testing or benchmarking.
To add to that, we also released the object analyzer pipeline. So we could use that to get much more detailed profiling data than other existing tools. So that could help find bottlenecks in not just in big data, but also any Java program.
Okay, thanks. You finally made the benchmark available, right? I've seen a link. Could you put the link on the screen again?
Could
It would have been nice to have maybe a short demo or something, but I guess now it's too late to set it up, right? Yeah. Okay, I see. Because when the paper was first submitted, there was not a link, so it's very interesting to be able to see the tool when people looks at the paper. So now we can see it. Is something you can show us quickly or not? I mean, we have 5 minutes if you like.
Samyak, do you want to associate into this one?
Yeah, sure. So it's mostly a command line tool. So
it's command line. Okay. Yeah. Then it's not needed. Okay, then, well, if there are no more questions by anyone, thank you very much. And we can carry on with the program, and we will start with our keynote and last talk of today. The keynote speaker is Connie Smith, and of course, a lot of you know her, but just in case, she was like a starter of software performance engineering. She has a couple of books on this area and a lot of experience. And now she's going to talk about before, now, and after, basically. So I'll let her start, please, Connie.
Thank you, Kati. Fortunately, I don't seem to be able to share my screen. I mean, I can click on share, but I don't see the application.
I'm sure you have a Mac, right? Because I don't have a Mac, so I cannot help you much because I guess it works differently. If you like, you could send it to me and I can share it, or I don't know.
Well, it's not in PowerPoint. It's in Keynote. So let me see.
Anyone that has a Mac, or I mean, we could use PDF.
It's a good thing we have the 5 minutes.
Yes.
Let me see what I can do here.
Connie, what happens if you share the entire screen?
Well, I'm not. Huh. Well, let me just try. Can you see now?
No, we cannot see.
Sorry.
No, it's okay.
Let me, while I'm working on this, let me try to save this as a PowerPoint and send it to you as a backup. It may not be, it may not have all of the things I wanted in it, but we might be able to see something. I'm sorry about this.
That's okay. It happens. We have time.
It's going to UIB at CAT.
Okay.
Okay, that's on its way. Can you see anything now?
Yes, now.
I'm seeing something very weird. It's got kind of a green box in the middle, but if you can see it, we'll just go forward with this.
We can see this, Connie, but this, yeah, the title is not seen completely. So I got your
Oh, I see. It's sharing a portion of the screen.
Okay, yeah, maybe that.
Let me try to change that.
Okay.
Okay, now it looks good. I think. Can you see it now?
Yes, perfect. Now it's good. Done.
Okay, now our time's up. Sorry. So what I wanted to talk about today is a little bit lighter. It's not so technical. It's about software performance modeling in the past, now, and what it's likely to be in the future, or some considerations for the future. It was inspired by a recent talk that Alex Podeko gave at CMG Impact 2022. And what he says is that maybe it's time to decouple queuing theory from software performance engineering. And this is a quote from his presentation. He thinks that while it was important, it's not currently the foundation stone. And that with multi-core servers and horizontal scalability and so forth, we're not really using 100% of the machines anyway. So maybe we should just leave those ideas to graduate studies and not have them be part of performance engineering anymore. And then coincidentally, in another talk for another CMG event, Boris Zabitsker has a different point of view. And he says in cloud migration, decisions are made without evaluating and looking at realistic performance and particularly financial expectations of these systems. And so he really thinks that we need to use these mathematical models, and particularly he uses iterative queuing models and gradient optimization to quantify these things. So who is right? And is it time really for us to move away from these overly technical models? So it got me thinking about it, and that was the motivation for putting this talk together. And instead of presenting to you the answer for this debate, I'm really trying to make some points about it and leave it to you. And hopefully we can have a discussion at the end about how you feel about it. Now, I am preaching to the choir. Most of the talks so far are about quantitative evaluation and using modeling approaches. So perhaps you fall in the second category and not the first. But let's take a look at some of the considerations. So the first thing is that in the early days, performance was really the focus of everything about computing. When people were building flight control softwares on tiny boxes, and it was a critical system, it was really fly-by-wire, lives were at stake. And so when they needed a change to that software, the first thing that they did was to put that change into an emulation or simulation of the system and test it out that way before it was allowed to be put into the software. Now we call those digital twins, and they are still around. They are not used to the same extent that they were in the past, as far as I know. Perhaps you've seen otherwise. So that was the way performance was managed in the early days. And the point about that was it was very labor intensive and expensive and time consuming to do things that way. And then IT systems and applications emerged. And we thought they were fairly large systems. We thought we had a lot of users. However, we thought a large network of users was about 100 people. But they were running on constrained platforms. They were running on mainframes, rarely with more than one processor. And the time it took to get a new mainframe was quite long. And so you had to make sure that your software would fit on those systems. And performance problems, if it fails, were actually a business risk. The business could fail if it was highly dependent on these systems. So at that point in time, these mathematical models were quite important to study software before it was built to make sure that you did prevent the performance problems. And the performance modeling tools, by and large, originated in the 1970s. And because the systems that these performance models were running on were fairly slow, it was the analytical approximation methods turned out to be quite important at that day and time. And I like to say that I got my degree at the University of Texas. You sort of got extra bonus points if you came up with a way to use analytical computing, queuing network models at that time. So that was then. Now let me clarify what I'm talking about these performance models. I'm talking in this talk specifically about the software performance models. So there's the ones in the top right of this picture. And at that time, and still actually, we use execution graphs to specify the software flow. What are the steps in the processing? What is the order of the steps? If there's looping or repetition or synchronization or communication with other processes, then you specify when and what order those things happen. And you could do an analytical solution of that. It was just a graph theory solution, and get some initial feedback on, will this idea even work? And for the applications back then on the machines they were running on, you could often get the answer just from that model that there's no way we can deploy this. We have to come up with a different plan. If your result was that things look good, then you went on to build contention models, and those were queuing network models that would quantify the performance of your new software that you wanted to deploy up in this software execution model. You could do measurements of existing work on the processors, put those into a queuing model, and you could get performance metrics that quantified the contention delays, looked at workload mixes, looked at scaling, and in other words, predicting sizing that application before it went into production. So those are the keys. It represents the software processing steps, and ideally it does it before you try to deploy a software system. So let's look at how these techniques were applied over time. In the early days, we focused on high-risk systems. Usually it was new technology, fairly sophisticated technology, very large software systems where you needed large teams of developers, and coordinating all of the software that was going to be deployed at once was a problem. It used what we thought were very large amounts of data and very large numbers of users. And when that set of conditions came together, then it called for fairly extensive labor-intensive SPE studies. And so the waves here show that this is Nazaré in Portugal, where they supposedly have the biggest waves in the world. When you had one of those big waves coming, then you applied a great deal of effort to make sure that you were managing performance. However, over time, things calmed down. You might have had new sophisticated technology initially, but as you gained experience with that technology, you developed some rules of thumb. You came to understand patterns and anti-patterns, and you understood the performance of that system, and it didn't require the same degree of effort. And so, therefore, it didn't require those overly complex, detailed queuing network models. And this last statement, unfortunately, I heard many times over the period of time when I was applying these techniques, when managers would say, we don't have any performance problems, we don't need performance engineering. They thought that they had a team of performance engineers and that that's what they were doing, applying the modeling and analysis techniques before software systems were deployed, when in fact they were by and large either testing things after the software had been developed and hopefully finding problems then, or they were finding problems in production and spending all their times doing what I call fix it later, which is don't worry about performance. When you build a system, you can always fix it later. And by and large, fix it later was buy more hardware. So that sort of stuck. So perhaps it is the case that Alex is in this latter situation, that the systems that he's seeing, they understand well. The technology that he pointed out is quite available. In cloud, we can just add more processors. It might take a few minutes, but that's nowhere near the 6 months that it took in the past. So maybe that's where we are, and maybe that's where we're going to be in the future. But notice this little wave over at the side of Nazarite. That wave could be developing into something bigger, and we might yet find ourselves confronting new high-risk systems as we invent new technologies and new applications. So we still don't have our answer yet. Now, the trend over the last 15, 20 years has been more to develop real-time embedded systems. And real-time embedded systems used to be the ones that I described, like the avionics application, when they were first doing fly-by-wire in the, at that time it was military planes. And at that time we had small scope, limited functions, monolithic software. It was actually fairly simple, relatively simple software. We had people doing the development who were quite experienced at what they did. They were writing in low-level programming languages with little or actually no middleware back then. And the real-time operating systems were fairly simple as well. Now we have a completely different situation. The number of control variables is quite large. Automation is large. We have many processors doing communication coordination. We have UIs. In general, things that we never had before. And so real-time embedded systems are a candidate for some of those risks. So now also we find software in almost everything that we have. It's whether we need it or not, it's in our refrigerators and washing machines and IoT devices and so forth. And hardware is usually not the limitation in these devices. We have modular servers, we have cloud resources that we can deploy as needed, and everyone is a software user. And we still have a great deal of tolerance about release 1 being deployed that has major performance issues in it. And people patiently wait for release 2. Most of the time, that's not always true. But so are we now in the situation that Alex points out? We have, in the early days, the performance models that we used were fairly complex and fairly manual. While we had tools that would solve them, it pretty much took experts to run those tools and to interpret the results. And so we've spent some time over the last 20 years trying to automate these and make them more accessible to more developers. So we've done things like automatically generating models from, in this case, on the right, we have UML diagrams that generate models. And we've had some of our people, Vittorio and other collaborators, have worked on automatically detecting and correcting performance anti-patterns so that you could specify a design in one of these model-driven engineering languages and automatically optimize that design before you deployed it. We've now, with the faster processors, we're able to use simulation solutions so we don't have the downfalls of the analytic approximations that we had in the past. Now remember, I'm talking about the software performance models before deployment, as opposed to real-time autonomic performance like Murray has been targeting. So analytical approximations did have some failures. They wouldn't always be precise enough when you had when you were operating near saturation, when you had certain circumstances with communication coordination. They wouldn't be quite as exact as we wanted. And so, you know, with reason, some of the software developers were skeptical of the performance modeling results. And the fact that we can now do simulation solutions viably relieves some of that concern, but not all of it. This is not, it doesn't solve all of our problems. So where are we going? What is the answer to the whether or not we need performance models in the future? And here's some things that dictate what your risk of performance failure are. Do you have a budget, or do you have an infinite resource? Do your CFOs still buy into just paying for whatever the cloud bill is? Do you have bleeding edge applications and technology? Because if you have something that you really don't understand how to model it, then how can the developers understand how to implement it effectively? So I think there's still going to be some of these challenges in the future. What's the tolerance of performance failures? Are the users likely to just shrug their shoulders and wait for release 2, or are they going to go on the market and look for a different product than yours? Will your CFO pay the bills? Are your stockholders patient through these periods of turmoil if you deploy something that has poor performance? And another thing that's come up that I think can be a factor in the future is how are we using our processors, our battery, and so forth? If you look at what they say about mining Bitcoin, the processing power required for that is really quite intense. And I am not at all patient with applications, cloud applications that I use that start firing up my processor and the fan comes on and the battery life drains if it's not plugged in. That's not okay with me. And I think that with the younger generation is going to become more of an issue than it has been in the past. So I think in the future, there can be more challenges that will still require SPE, and it will still require these models. So model technology tends to lag behind software evolution and processor evolution. So as we come up with new applications, we have to create the models of that new application and new software. And those models are most needed when the performance effects are not well understood. And so when we have these situations, we often have surprise performance problems. They weren't anticipated because we've been coasting along with technology that we understood for years. We have performance people on staff who are doing performance testing, and we don't expect these problems to emerge. And all of a sudden, when you try something new, you are surprised by these performance problems. So that just says that performance engineering has not predicted them for us for various reasons. This has always been a challenge for me as a performance engineering practitioner, because I was called in on these new novel applications, and people recognized that it was going to be a technology challenge. And they bought some insurance and brought people in to do the performance engineering studies and to predict whether or not it would go smoothly or if they would expect performance problems. And I was always uneasy doing models of things I had never done before, and then saying with certainty that it was going to be problematic or it was not. And you know, I don't think there's a fix for that other than to anticipate what the new technology is and to start studying it in advance. It'll be always a challenge. And I am still of the opinion that modeling needs to be easier and it needs to be automatic. We need to be able to predict the performance, and we need to be able to quantify alternatives in a way that a non-expert can look at those results and make some conclusions about their software design and implementation before it's deployed. That's still going to be a challenge. And so these overly technical models and representations of models like execution graphs, like layered queuing networks and so forth, are not going to fill the bill for that kind of use. It will still always play a role for these emerging technologies, I believe, but it doesn't work for these easier automatic models. One thing we can do is to recognize that we don't know how the systems are going to behave once we deploy them. And so we can build and deploy some self-adaptive systems that can be tuned. Like, for example, if we don't know how long it's going to take to encrypt, this is hypothetical because we can't predict that, but if we don't know how long it's going to take to encrypt a user's query, then we can build in some tunable algorithms and switch between those at runtime once we find out how long it takes. I'm sorry, that was probably a bad example. But I hope you get the message that we can anticipate the things that we cannot quantify at design time and build some different plugins that we can invoke at runtime when we find out what the situation is. So I think one opportunity that could be explored more is to use more machine learning, and this is for developing SPE technology. One thing to look at is what is the performance of those machine learning algorithms. I don't think that's the interesting point here because they are what they are. We would like for them to be amazingly fast so that we can use them at runtime, and in particular to use them for autonomic performance management at runtime. And I saw there was a tutorial yesterday on this. Unfortunately, I missed it. I'm hoping I can go back and look at the video of that and learn more about how that's being used. That's one application. So that would say that you can worry less at design time about performance because you can tune it at runtime, automatically tune it at runtime, not by sending in firefighters to solve the problem for you. What about using machine learning to learn about what performance requirements should be? In the 90s, I believe, there was AppDex was a technique that was a measurement-based approach to quantify, essentially quantify the patience of users of applications and to rate whether your software is meeting those expectations. Is it in the green? Are they happy? Is it in the yellow? They're patient, but only so patient, or are you just unacceptable in your performance requirements? So they would look at large at that time, collections of users of various applications, and they would measure response time, and they would come up with measures, quantitative measures of how well you were doing with your performance requirements. Well, I think we could use machine learning to learn some about what our expectations should be so that we can specify performance requirements at runtime. See, that's always been a limitation of performance engineering. We could go through and build models, we could use the queuing models, we could get our performance quantitative metrics out of those models, but how good are they? If you haven't specified performance requirements to begin with, then you can argue that, well, maybe that's okay. It's not the few seconds that we hoped, but maybe that's fine. And if you have quantitative performance requirements, then you have a lot better chance of managing performance expectations. So I don't know how to do all of these things, by the way. I'm just suggesting that I think that we could take a look at this new technology and make some headway on being able to solve some of these problems. Another one is in the models themselves. And so I think machine learning could help us quantify future workloads, quantify the workload mix, quantify the volumes that we might expect. I think we might be able to predict characteristics of transient conditions. And if we can predict these things, then we can put them into models and we can study them and come up with good solutions. But in the past, we've not been able to effectively do some of these things. Now, another thing that I think, because of my background, obviously, is that predicting performance resource requirements prior to implementation, before we have code, before we can measure it, what are going to be the resource requirements of this software has always been the most difficult part of creating these performance models. And so I think that we could use machine learning to help us in advance quantify and predict some of these things that we could automatically feed into the models. And let me just show you a couple of things that explain this last comment. On the right, I hope you can see it, is one of the techniques that we used early on to help developers specify what it would take for their software that hasn't been coded yet to execute. And we found that we could reduce it to things that they did know about. They could tell us, for example, how many messages they were transmitting. They could tell us how many times they were accessing the database. Work units was kind of a workaround that we used to help them estimate CPU requirements. So they could tell us that it was a trivial task, it was moderately complex calculation, or it was an extremely complex calculation, for example. Or maybe we could even have a 1 to 5 rating. And then we could plug in some what ifs for those CPU times, and we could plug all of that into our model, and we could come out with the results. But you can imagine that just coming up with those numbers was quite an effort. We came up with specifications for how you do a walkthrough to pry these numbers out of developers and so forth. But what I'm saying is that perhaps we can get these things through machine learning of applications that have been developed in the past. Let me show you one more slide that helps to explain what I mean by what we need in a little more detail. This is, in fact, a sequence diagram of one in particular machine learning algorithm. And if we wanted to predict the performance of this algorithm, then we need to know, or for these loops that we go through, how many times do we need to go through that loop? We need to know there's a weight calculation down in this region. We need to know what's the CPU time for that weight calculation. For the distance calculation down below, we need to know what's the CPU time for that distance calculation. And if we have one of these running, then we can measure it. But presumably, these are going to be different for different workloads, right? So how could we use machine learning to come up with some of those values to automatically feed into a performance model? So now, let's go back to the original question. Are we done with queuing theory, or do we need to teach this queuing theory to students in the future? And here are some possibilities. I think whatever, if you have a performance engineering curriculum, then at the very least, we do still need to be teaching about SPE models and what they can do for us and what they don't do for us. And we can teach basic understanding of modeling technology. We can teach simple things like Little's law, utilization law, some queuing modeling basics, and how to understand and interpret results. And so the idea here is to give new performance engineers just enough information to know that there is a resource available to them, but not necessarily to be able to use it for nuclear power plant software evaluation. But we would like for them to understand that there are models, that they can be used, when they can be needed, when that big wave is coming and they should be worried about it. And we should also convey the model viability and what the weaknesses are and when not to trust the results. And then assuming with this knowledge, very basic knowledge, they would at least know enough to call in some performance engineering specialists who could help them tackle the big problems. There is still a role for this technology depth, because remember, we're always going to be challenged with things that we don't yet understand. We need models and we need understanding, quantifying performance of things that we don't know about yet. And so there is a need, I think, personally, for researchers to help us evolve this technology, for researchers to be looking at the bleeding edge applications in technology. And therefore, I think we do need to be teaching queuing networks theory, personal opinion, to at least some subset of the performance engineering community. Maybe your everyday performance engineer doesn't need it. And another question addressing Alex's concern is, do performance testers need to know about performance models? So I was really not providing you with answers. I was just trying to raise some of the issues to show what we've done in the past and what its limitations are. And hopefully to get some opinions from you and the audience on what you think. Do we have an invention that makes queuing a thing of the past? Or do we still need to be teaching it?
Thank you very much, Connie. Very nice talk. I really enjoyed. Okay, so let's see. Anyone has any thoughts here? Any comments, questions?
I have a few comments, if I may go first. Thank you, Connie, for the great talk. I found the subject very engaging and interesting, and I agree with the fact that this, the relevance of queuing is not as clear as it was a few years ago, and there are solutions like, for example, machine learning that can bring new perspectives in problems that we have been attacking until now with queuing. I just want to mention briefly that one of the points in the tutorial you referred to that we were making that is relevant to this discussion is the fact that even if you use machine learning methods, deep neural networks, and so forth, these are methods that essentially need to are data angry. They need to be fed continuously new data, and therefore our point in that tutorial was that it's important to pair machine learning methods with a simulator alongside to essentially explore and give say out of distribution information to the neural network. So my personal view is that there is not as much tension as we perceive between machine learning and say model-based methods. Actually, they can coexist, but perhaps the role of models could be more to generate data and that is fed into the machine learning methods or surrogate models. And just a final comment, I strongly agree with the point that it's important for engineers to understand the systems, and therefore to me, we should keep at least the teaching simulation. We should keep going, because the art of modeling and the art of, say, analytical evaluation are two different arts, in my view. They work together, but the concept that you can abstract a system and reason on the on the concepts is still very relevant, important, and worth teaching, in my view.
Thank you. I totally agree. I like your point about using the models to generate data, because I did forget to mention that getting the data for researchers to use to do these machine learning studies to quantify performance requirements, to quantify resource requirements, is going to be a big challenge, because you need access to real systems, or as you say, to models of real systems, which it's a good way to make it viable. Thank you.
Connie, I'd like to introduce a point about the evolution of the way development's being done. It seems to me quite a bit of it is trying to deal with performance problems through the process, rather than having to actually study the performance problem. You find ways to manage it or avoid it. And one of them is adaptive management, which adjusts the resources to adds more processors, fixes it later, if you like, without intervention. But the other one is event-based systems. I've been looking at these lately. It seems to me that it's all driven by a desire to avoid performance problems, getting rid of synchronous communications, and it substitutes high overhead and other latencies for messaging. But the whole philosophy is, I'd say, to get rid of synchronization. You can't synchronize two event-based processes because they don't know who they are. They just talk to each other through an interface. And the stateless services. So there may be problems inside one of these services, but that's a more limited, it's not looking at a system-wide performance problem there. In some ways, I think event-based architecture kind of, it puts bounds on performance problems that it could be maybe the new normal. At the cost, I think, of more expensive execution, probably. And things like, in our performance models, I don't think we've ever dealt with things like polling terribly well, because the polling methods all require different models, and they introduce significant delays. Well, a lot of message-based communication now in these event-based systems is polling. You poll the message queue manager to get your messages. And these delays are not they're not straightforward for us to include in models if we wanted to build them.
Interesting points.
So maybe we're being made redundant by design. We're being undermined by the software architecture and innovators.
Right. Yeah, we solve the problems and then they figure out another way to have problems.
Yeah, but maybe they can reduce the number and variety of problems so that they're easier to cope with. By making some things illegal, like if you have only REST interfaces, you limit the kind of interactions you can have. It simplifies the process of classifying workloads. And
yeah,
I don't know.
Andre, you must have something to say about performance requirements.
Not only about performance requirements, but about modeling in general. The event-based stuff is not going to do away with the notion that nothing comes from nothing. And you still need performance requirements there too. But one of the misnomers that one of the misconceptions that I found is that giving priority to something actually makes something faster. The total amount of work done needs to be the same. And whether you're using event-driven communication or synchronous communication, you still have conservation rules at play. And I think the developers and the testers need to know about that. Unfortunately, I'm missing Alex's talk right now. You mentioned his decoupling queuing theory from whatever, but that assumes that we can structure tests that are going to tell us as much as the structured tests that are based on the operational laws can tell us. The unstructured tests are not going to reveal trends, and we need those trends in order to understand where things are going to break down. Because it's the deviation from those trends that actually tells us whether there's a synchronization issue or a thread safety issue or something like that. And yes, priority queuing will do one thing for you. It clears some. It may be useful to have it to clear memory-intensive transactions, because then you can get rid of the memory quickly and free it up for something else. And somehow or other, we need to find an avenue to get that point across. But the issues in which that arises are often so specialized that it's difficult to find a good time to get that across. There needs to be a cadre of people who still have that expertise and who can build bridges between that expertise and software engineering and computer architecture generally.
Yeah, resource constraints will never go away. Will always be important, and I think that some understanding of queuing is necessary to understand them. But a lot of the problems that Connie was raising, the bleeding edge type problems, are not just due to raw capacity requirements. There's some protocol that has a lot of intricate message exchanges that just takes too long.
Yes, I agree with that.
It's these special mechanisms that get introduced in new systems, and they're hard to model, and they don't fit into our contention models all that well. That cause us a lot of the grief.
Maybe we can model them with state machines, talk about the amount of time to transition to one kind of state rather than another. Sure.
An individual mechanism may be modeled by, like a protocol, may be modeled by a state machine, but it has to fit in with everything else. Delays just to change states depend on contentions. So
sure.
It's some way to piece together a more modular approach, which can combine state models and contention models. And I've tried to build a system like that around the layered framework, and it gets very hairy and clumsy. And Petri nets are wonderful for this. You can model anything with Petri net. So Petri net models are never defeated, except maybe by how long it takes to solve their models. But they can always make a model. It's a great framework for that. I just gave up on it because the models, when you get to 10 to the 100 states, you just can't handle it.
Can I say something? I would like to start from the question whether it is necessary or not to teach QE network, I mean, to software or to future performance engineer. I may be old enough, but I think it's still necessary because of understanding how things work. Beyond the fact that QE network can be used or not, but as Connie was suggesting at the last slide, little slow utilization, low parameters and indices and their own relationship in the systems, they can be understood only if you study them. I mean, if you teach them to people, and then people connect. For example, like Connie was showing, number of visits to the role of software in a complex system. Otherwise, you can use even sophisticated tools for analyzing performance in systems, but in order to, to interpret results, people need, even young people, they need to know these foundations for sake of being better, I mean, interpreting results and understanding performance. So I still think we need to teach basics, even though in my master degree class on software performance engineering, when I have Blackboard and I explain some operational laws, those 2-3 lessons, they are boring for half of the class because it's mathematics. They don't expect in a software engineering course to have some mathematics, very simple, but the half of the class is bored. But I think it doesn't matter because it's necessary for understanding, for having good foundation in the field.
Yeah, I agree with you 100%, Vittorio. I would say that probably the most important aspect of teaching elementary queuing networks is having people grasp that there's a bottleneck somewhere, that there is going to be something holding something back, whether it's a hardware bottleneck or a software bottleneck. A software bottleneck could arise just because you don't have enough memory partitions or something like that, so you make big N or big M very small. It also has implications for load testing because you need more load generators to drive more throughput through a system. So it makes big M very large, and the think time in the load generator is going to constrain the throughput. So the question we need to be asking is, I think, how do we get the point across that there's always going to be a constraint of some kind, and how do we help the students identify where that constraint is?
But I think your point there, Andre, is that this isn't stochastic processes that's important. This is more the physics of what's going on in the system flows and things like Little's result. But stochastic processes are not the essence of what you were just talking about.
I agree.
I think the stochastic processes that Alex Padelko was saying are not essential. And that's a more sophisticated question.
As they might say in German, Jein, yes and no, because because variability can really mess things up for you. Even if you on paper you have enough resources, in utilization terms you have enough resources allocated, variability can really mess things up. And it's a mismatch between sequences that causes the queuing in the first place. It's variability that causes queuing in the first place.
Sure, but if you model variability by an exponential process, which is the way everybody starts out, well, this may be a decent model for it. It may not. It may not have enough variability if you've got some long-tailed process. So you may underestimate the impact, or it may have too much variability. We do it because it's tractable. If you have only slight variability, you may have a different kind of process where almost everything is deterministic and you get the occasional outlier. Well, an exponential distribution doesn't really help you understand that.
True.
So
simulations would.
Only discrete event simulations would. At them. I don't know. You have to look awfully closely to understand what's going on in a discrete event simulation like that.
And to verify them too.
Yeah, people don't usually. They don't want it for that.
No, I like looking inside discrete event simulations also because what they reveal about transient behavior.
I think you can get people to start thinking about flows of transactions rather than just the processing of one transaction. You've already made a big step towards thinking about the system. when I was teaching undergraduate students about performance engineering, they had a couple of aha moments. And one was when they first ran a profiler and understood that they could actually measure this stuff, that there were numbers which they could get out about what was going on, because they never thought about how long it took to do anything. It just isn't part of what a programmer thinks about. And the other was when we looked at Little's result and bottlenecks, and the sort of the force of flow through a system and the limitation somewhere, the sort of thing you were just talking about. But it's a combination of the force flow law and bottlenecks and Little's result. There's a lecture there that I think is probably key to a lot of the problems.
Can I add another moment, Murray, that happens in my class?
Sure.
Another aha moment is when you formulate the total demand to a service center as a combination of visits and service time, you know, and you decouple the two aspects. And you decouple the aspect by attributing visits to software and, you know, for example, and service time to hardware. And you have a decoupling, you know, and of modeling. And that's an aha moment, because some of them, they understand, like Connie was saying, like software modeling is important because you separate issues, you know, between the software and the hardware. And it's inside a simple definition with numbers that quantify the two sides of the story. And that's another moment that sometimes makes some light in few students.
Absolutely.
Peter Denning used to talk about how page virtual memory would make the whole bottleneck configuration break down. Those weren't the words he used, but following along the lines that you're discussing, Vittorio, he would say, okay, the system is starting to thrash, so the VI of the paging device is going to go sky high, and that's going to drive the throughput down. So the system would basically grind to a halt because of the thrashing. And that's why good page replacement algorithms were so important. But people don't necessarily see that now. He was teaching this at the time when mainframes were all the rage, and the idea that we'd have as much hardware on our desks or in our pockets even as you have in a PC just wasn't known. As you'd have in a mainframe just wasn't known at that time. It was inconceivable, but you can see the same problems occurring here. Also, I don't know about your PC, but mine gives the lie to the system that the CPU is always at fault. I have a horrible time with the web when the disk is 100% busy because the browser can't cache. And if students experience that, I'm sorry, Puyan, you were going to say something?
Something quick after you.
I'm done.
Please finish. Yeah, I wanted to say thanks for the keynote. It was excellent. One observation that I had was that, you know, recently after ML boom, people started using mainly ML, even unjustified models like deep neural network for performance modeling, which, you know, for simple system where if you look at the data, it's kind of linear model is sufficient to model that, right? I mean, these type of ML models are useful when, you know, you want to have a complex systems and you don't have some white box knowledge about the system architecture, internal of the system, source code, etc. But one thing that could be useful is basically best of these both worlds by combining these two, like queuing network and ML. When we have some sort of knowledge about the system, source code architecture, internal of the system, we can model it through queuing network, but sometimes it doesn't scale, right? Where we can fill the gap by ML and some sort of using data to give us a better prediction.
One of the disturbing things I've found in trying to fit queuing models to data is that if you take the data from a queuing network, and I've done this with simulated networks, so I knew what I was getting at, you can't really infer the parameters of the whole network from the way the system behaves. The data really only resolve to 2 or 3 queues, and the rest of it gets buried. They don't, most of the servers don't have much effect on the system because they're not heavily enough loaded. So you're basically modeling only the bottleneck. So if you model from data, you're modeling the bottleneck. You make a change, now the bottleneck moves, you've got to make a new model from data. So modeling from data is rather limited in its ability to get insight into the system, unless you have probes into all the servers that model them well, even when they're lightly loaded, which seems to be the answer for getting better models.
Well, you've hit on the point that I find most perplexing about machine learning of all, and that is that the models that they use seem to be completely decoupled from the mechanism.
Yes, they're curve fitting models.
Yeah, they don't tell us much about what's going on inside at all.
You go back to the 60s and people were writing analytic models for performance are regression models. You fit a quadratic curve to this response time, and that's your performance model. That's machine learning, only it's more sophisticated than quadratics, a bit more sophisticated.
You can fit more curves and it does it for you, but you still it still doesn't tell you. You still need some insight to figure out what's causing all that.
It doesn't tell you causality, really. They give you correlations.
Right.
That's about all.
I think you have to tailor what it is you're using to drive the machine learning. If you feed in the proper things, then it will give you the right curve out.
If you can get, you have to go deep into the system to get deep structure out. Yeah.
Or you need to make sure that your classification is working properly.
Yeah.
Exactly. These are all fun issues to study, don't you think?
Yeah, Marion Latoya and I were looking at Kalman filters to track performance model parameters as systems varied. And Marion did some experiments with a grad student on Amazon. And he said that he could never really successfully track more than a 2Q model. If you modeled, in fact, one queuing center and one delay center was enough to model most systems. That's the bottleneck and everything else, basically. And the statistical significance disappeared if he tried to construct a model with more servers, which was disappointing because he was hoping, and I was hoping, that we'd be able to see the deeper structure of the system through the response time behavior. But it doesn't get through because there's so much randomness in the execution of the, I mean, there is really a lot of randomness around due to caching and network delays and what have you. And it's worse in clouds.
That's interesting. That says that we need to publish some things that we've tried that didn't work so that people don't waste their time studying those.
It's a good point.
How do we go about that?
Referees wouldn't like it.
We could start a journal, the Journal of Bad Performance, or Bad Performance. Yeah.
Things that don't work.
Something like the Journal of Irreproducible Results, but for our field. You know, there is such a journal.
I know.
Yes, but we can reproduce the bad results.
They're still bad. Yeah.
Well, I don't know if anyone else has something else to say. Just one thing that is always a thought for me when I teach, because I basically think like Victoria, that these basic performance issues, I think they need to still to be taught. But what I'm trying to think about sometimes is how could we teach them so as they're not so boring for the students? But it's a difficult answer, I think. Maybe it will be more part of this like teaching related workshop, but it would be nice.
I have to show you my Oktoberfest example sometime.
Yes.
Actually, there's another problem with teaching these things, and that is that those of us who learned these in the old days, you know, learned all the fundamentals, but the people who were looking at to teach these things in the future don't have that background. And so how do you teach the teachers?
What are you thinking of in terms of background, Tony, that's missing?
Well, I think if you go to a model where you only teach the high level things, like I showed on that last slide, then you have a whole group of people who only know those things. right? And like, for example, let me plug Andre's project that he's working on with Ye at Stevens Institute. They're working at how do you teach performance engineering to the kids? What topics should be there and how do you teach it? And
we have an NSF grant that starts in June.
Yeah, and I think that's very important work. And I think developing some materials is going to be very important, because I am all the time approached by people who have read my book and they want me to send them their lecture notes so that they can teach from my notes to them instead of developing them themselves. And we're losing that expertise. And so I think we need to start compiling some of these materials for people to teach performance engineering in the future.
That's good.
I think they're in the OR department, Operations Research Department, or in the math department.
Yeah, you
and they don't talk to us.
I think we made a mistake not continuing to publish in that venue. Some of my early publications, and I noticed Andre's as well, were at ORSA TIMS, Operations Research. And perhaps we should have kept down that avenue, and maybe we should go back.
Well, thank you very much. I think they're all were very interesting comments, and it's more or less about time to finish. When I was thinking about this workshop, I thought about the past. So the very recent past is what is being told at the beginning by Daniele, but I just have a few slides related to a past a bit farther away. So I'll just show them to you. Let me see. Can you see it now, right?
Yes.
Yes. Well, so Wasp started in '98 with Connie and a few others that you are here now, I think. And well, I thought I would have many photos of these conferences, the ones I've been, I was not there in Santa Fe, but I went to my files and I couldn't find so many, but still I do have a few. So I thought, since we cannot see each other, I just put some photos of our like fun times at past conferences. So this is Palma in 2005. Let me see what else I have. Yes. I don't have as many as I would have liked to, because I have much more memories than this, but those are the photos I could get.
Nice.
Well, after Wasp, we joined with Wasp CPU and we started with ICP. So this is the starting of it. After now, I could find these ones from L'Aquila, and that's about it. But I think you enjoy them. And well, thanks to everyone. Thanks again to the authors, program committee, and to the co-chair Daniele, and to all of you, and hope to see you soon. And hope is not online next time, and we can see each other maybe in Portugal when the next ICP.
So that's the meaning of your pictures, right? There was a time where we were sitting beside each other, and there will be a time for being again, you know, there.
Yeah. Hoping.
We should have taken some pictures of the screens for memories of the online conferences.
Not at all.
By the way, there's a workshop on, there's a discussion on education in which I'm participating in LTB in an hour's time that Alex is running.
Right.
Okay, so maybe we can see each other there.
Yep.
Okay.
Thank you so much for organizing this.
Yes, thank you, Kathy. Thank you, Daniele.
Thank you, bye.
Thanks.
Arrivederci.
Thanks.
Arrivederci.
Bye.
Ad-
Ciao.
Domani. See you tomorrow.
Bye.
Okay, bye-bye.
Bye.
Bye.
Okay, thank you, Daniele. I'm closing the session. Bye.